and Lorentz force. So we will start by the idea of magnetic field, what it is, what's the concept behind it, then we will define it. We will then talk about forces on moving charged particles, then how those charged particles move in different patterns when influenced by magnetic fields, concept of cyclotron, velocity selectors, influence of both magnetic and electric fields, then force on current carrying wires, and then we will take a loop and make it into a magnetic moment. Then we will find the torque and energy on it, and finally we will end the class with gyromagnetic ratio. So that is the flow of today's lecture. Alright, I hope I am audible, visible to all of you. Let me know quickly in the chat box, and welcome to the next amazing class. If you have not yet watched the previous lectures, please do watch it, because it's going to be very useful for your either coaching tests or your self-study preparation, for your mocks, and in general understanding all the concepts in details. Okay, so let's begin. Ready for it, my dear warriors? Alright, Vaskiju, welcome. Let's begin with the class with the first concept of magnetic field. We have studied what electric field is, or electric lines of force were. It was defined as the force which was acting on a unit test charge which is placed in the vicinity of some other charged body. Same way, magnetic field also is created by different objects which are magnetic in nature. Example, a simple bar magnet, or even a magnetic compass or a needle like this, or you might have seen some gadgets. Even your phone is magnetic in nature. Even a lot of devices, your laptops, your so many wall clocks, so many places you will see teeny mini magnets here and there. So even our earth is basically a magnet, by the way. All these things are the sources of magnetic field. Like an electron or a proton is a source of electric field. It creates electric field around it. Same way, the earth has its own magnetic property, and it makes sure that it will either attract, repel magnetic objects around it. So it creates a magnetic field around it. A bar magnet also creates a magnetic field around it. A magnetic needle will also create. Even you might have seen fridge magnets. You go travel somewhere, you buy those nice fridge magnets, right, as a souvenir, and you stick it on the your refrigerator. Those also are magnetic in nature. Now these magnetic properties were actually discovered centuries ago, but that time they did not know so much about it. Slowly these ideas developed, and then Maxwell and Biot-Savarts and so many other people, Oersted, all these people slowly contributed in the understanding of the nature of magnetism. And that's how we know the way magnets are and the fields are as we know today. Okay, so let's begin. Yeah, I will be taking it from scratch. Yes, hi Ganesh, my voice and video is clear. Okay, hi, stay happy, welcome aboard. Just to show you and make you visualize, I have this simple simulation. You can see this bar magnet out here. You can see this is a detector of the magnetic field. You can see this is actually a compass or a needle, and a compass or a needle, we use it for navigation purposes, and it has been used since long time ago by ancient navigators, right, to find different places around the earth, so via the sea. So this is a simple magnetic compass, and you can see the magnetic needle will change the direction. Basically it always tries to align itself in the direction of the magnetic field. This bar magnet, it's creating its own magnetic aura, or the field, its presence being felt. Right now the strength is just 25%. If I make it slightly larger, you can see it becomes brighter. Basically it shows that the magnetic field has become stronger. Alright, so reducing the strength is reducing the intensity of the field, increasing it is making sure the magnetic field is now stronger. This compass is always going to point in the direction of the magnetic field depending on where I am going to place it, and you can see these are the magnetic fields around it. If I flip the bar magnet, you will see the magnetic field will also flip. You might not see it so clearly, but actually if you observe keenly, the white and the red icons will flip. Observe as I flip the magnet. The red becomes white, the white becomes red. Even the magnetic needles behaves the same way. Whatever is white will become red and whatever is red will become white. So that is what changing the polarities of a magnet does. Like I said, even Earth is also a magnet. It's a huge bar magnet and it is also having its own magnetic field around it. And that's how we were able to navigate from one country to the other country using this concept of magnetic field. Even so many birds use this technology by nature, by biology. Okay, so that is what it is. By the way, a lot of people think inside the magnet there is no magnetic field. That is absolutely wrong. Even inside the magnet there is magnetic field. So a lot of people think the magnetic field is only around the magnet. No, in fact it continues within the magnet, and that is going to be a very important aspect. Are you now able to visualize what a field of magnetic body is, what it means, and these polarities are going to decide the direction in which the magnetic field is going to flow. We will talk more about these polarities in the other chapter, but you might have a vague idea. Just like in electricity you have positive and negative charges, same way you have two different kinds of magnetic charges. One is called as the south pole, one is called as the north pole. They are exactly opposite but somewhat similar. We will talk more about it in the next chapter. We will not focus so much today. Just that you would know that north and north or south and south will repel each other, and the opposites, meaning a north and a south pole, will always attract each other. So it's always the opposites which attract, and you might have seen that very very much even in movies, right? The hero will be somewhat and the heroine will be somewhat, two opposite characters, but they will fall in love. Same way over here in magnets and electricity, the opposites will fall in love, and the similars, right, will be besties. They will probably not be very close, but they will repel each other. So the similar things will always repel each other. That's what is true in magnetism as well as in electricity. Now let us learn about, first of all, the properties of the magnetic fields. Some of them are pretty much common to what you have learned in electricity, but I feel it is very important that we know about it right now before proceeding ahead. Okay, all right. Rahat, you can search for me on anywhere, Captain Shreyas. All right, Captain Shreyas, anywhere, Telegram, Instagram, anywhere. All right. Hi Piyush, good evening, good evening. All right. First important thing, if I show magnetic field lines like this, if I show magnetic field lines, magnetic lines of force, these are your magnetic lines of force, that is what we call as the magnetic field. That is what we call as the magnetic field. If I draw a tangent to it, at any given point, that particular tangent gives me the direction of the magnetic field at that location. So at this place, I know the tangent can be drawn this way also, that way also. That's why these arrow marks become very important. So this is the direction of the magnetic field. Now the symbol of magnetic field, remember, is a B, and it's a vector quantity. So you put a bar or an arrow mark. All right. So obviously it's a vector quantity. It is obviously a vector quantity because it has magnitude as well as direction. So this gives me the direction. This also means that just like in electricity, you cannot have two magnetic fields intersecting each other. So this is not possible. So this is not possible. So magnetic fields can't intersect. They can't intersect because if they do intersect, that means there are two tangents. And if there are two tangents, that means there is no uniqueness, there is no unique direction. And in physics, you cannot have such things. There is always a unique direction for a vector. You cannot be confused. A vector is pointing this way also and that way also. No, a vector has a very unique direction and a magnitude. So that uniqueness is lost the moment you draw two or multiple tangents because of an intersection. So this is not possible. This is basically not possible. Keep that in mind. This is basically not possible. Just like in electrostatics, the closeness of the fields used to talk about the strength of the field. Same way, you will see if the magnetic field lines go somewhat like this. Here they are closely packed. So then I will say the field is strong. I will say the field is strong over here because the field lines are very much close. They are dense over here. They are very dense over here. Whereas I will say the field is weak over here because of the reason they are very far away from each other or they are very sparse, meaning they are not dense. It's the opposite of dense. They are not very close to each other. But what happens, sir, if the field lines are parallel to each other? If the field lines just so happen to be parallel to each other, then it is said to be uniform field. It is said to be uniform field, right? Just like in electrostatics. But this is an example of non-uniform field where the strengths are going to vary. Most of the times the fields are going to be non-uniform. But yes, you can get uniform fields by small arrangements here and there. Like over here, you can see the field lines are very close to the poles. But as you go far away, the intensity, the strength of the field will reduce. So close to the magnet, the field is very strong. The field lines are close. But as you go far away, the field lines go away and the field becomes weak naturally. Alright. The next important thing is that, and this is the most important differentiating factor, guys. Keep this in mind. Magnetic field lines never really originate nor do they terminate. This is very unique. Magnetic field lines, they are not going to originate, they are not going to terminate, meaning they don't have a start, they don't have an end. It is always closed loops. So very, very important property. Magnetic fields are always closed loops, meaning if I take a magnetic field somewhere, it has to end at the same place, like this. So if I take another magnetic field, it will be probably like this. That's it. This is how magnetic field lines are. If you probably show something more inside, maybe it is like this over here. So these are basically closed loops. This is what is actually there. This is what happens. But this is not going to happen, meaning you have a magnetic field starting at a place and ending at a place, or magnetic field starting like this and abruptly ending over here. All these are not possible. All these are wrong. So these things have a start and an end. These are not closed loops. This is not what you see in magnetic field lines. Now you might wonder, what is this? Why is this happening? So I'm going to blow your mind right now, because what I'm going to tell you today, or what I'm going to tell you now in the next 1 minute or 2 minutes, you will change your perspective about North Pole and South Pole, and I bet that nobody would have told you about this in this manner. Okay. Say for example, when we show a bar magnet, right? When we show a bar magnet and we say that this is North Pole, this is South Pole, and then we show magnetic field lines, maybe starting from the North Pole and ending over here. Now you might have wondered, sir, in a bar magnet, though, I used to show it like this, sir. So it used to start in the North Pole and end at the South Pole. But actually it is wrong, because it actually doesn't start at the North Pole. Inside also there is magnetic field and it is the continuation of that line. There cannot be abrupt end or start. In fact, this same line will continue like this inside the magnet. This same line will continue inside the magnet and even outside. Yeah. So there is no abrupt end or start. In fact, I can take any other such line. Even if you take it here, it will be like this. You will see it is always going to be closed loops. You will say take it here, also it will be again closed loops. So this is how exactly a magnetic field line is. It continues its journey inside and continues its journey outside and again returns back. So that is how the magnetic fields look like. But then, wait a minute, till now I have not yet made that surprising statement. But then, I know you might be wondering, sir, we used to think that North Pole is the emitter of magnetic field lines, South Pole is the absorber of magnetic field lines. Correct. Now, look at this. Imagine I draw some random magnetic field line somewhere. Doesn't matter what the shape is, etc. Chumma some random magnetic field lines I have drawn somewhere. Where is the magnet? I am not sure. But I know 100% that this is a magnetic field line because it is a closed loop. Now just imagine, for now, I take this as my magnet. I take this much part as my magnet. This orange shaded part. Okay. For that particular magnet, which is generating this magnetic field lines, because I see the field lines coming out from this side, so for this magnetic body, I will call this side as the North Pole, and because the field lines are entering on this side, I will call this as the South Pole. But let's say the same field lines were being emitted due to some other body which is over here like this, Say that particular body was emitting these same magnetic field lines. Because from this side the field lines appear to originate, so this side I will call it as north, and because the field lines appear to terminate, I will call it as south. So this concept of north and south is just a relative term on this magnetic field line, if you notice. If your magnetic body is here, this is north, but if your magnetic body is here, then this same region becomes south. So on a magnetic field line as such, there is nothing like, sir, is this point north or is this point south? It could be anything. If it is on this side, the body, then this side will become north. If the body is on this side, then this side will become south. So understand, this concept of north and south depends on where your body is relative to those field lines, and accordingly one of those sides becomes termed as north and other called as the south. Are you getting my point? So technically speaking, I can draw many such north, south. There is no such restriction on me. I can draw as many such magnetic bodies on this particular closed loop. So there is no point only of literally showing this north and south, because north and south is a relative thing depending on where your body is placed. So the concept is that your North Pole and South Pole are mere fictional characters or imaginary characters, you can think of it like that. Actually, such monopoles do not exist. These kind of monopoles do not exist. Magnetism always exists as dipoles. Di is 2, mono is 1. Poles are polarities which are of opposite nature, basically in this case the signs. Electricity has 2 polarities and they can exist independently. I can have a simple negative charge, I can carry it anywhere I want. There is no restriction that if you take a negative charge, you have to carry a positive charge. Same way I can carry a positive charge, which is a proton, anywhere. There is no restriction. Sir, you took a positive charge, you have to take a negative charge along with it. No such thing. So I can take individual charges of any sign, positive or negative, whatever I want to do, I can do with them. But in magnetism, you cannot just say, I want south. If you take south, automatically north comes. If you take north, automatically south comes. Because if only North Pole existed, then field lines would have originated from them. But that never happens, because the field lines are continuous. You will see that the field has to come from somewhere, and that will be from south. So within the magnet, there will be some traveling of those field lines. So you cannot just have a single North Pole or a South Pole. In fact, if you notice, within a magnet, inside a magnet, the fields actually travel from south to north. But outside the magnet, they travel from north to south. So, because the field lines have to be continuous closed loops, you have to get a south with a north or a north with a south, meaning they will exist as two polarities, two opposite natures as pairs always. You cannot separate them out because a single polarity cannot exist in isolation, cannot exist on its own. It has no meaning. So they always come in pairs. If Pandu comes, Champa will come. If Champa comes, Pandu will also come. Pandu does not leave Champa, Champa does not leave Pandu. Here Pandu and Champa means north and south. Is this absolutely clear? Okay. Yes, Ayapan, I am here only, man. Yes, field lines are non-uniform. This is the best example, bar magnet or Earth's magnetism. The field lines are non-uniform. Near the poles of the Earth, the fields are very strong, and as you go far away, the fields become weaker because they will spread out in a vast region of space before again coming back near the other pole. Are you now understanding? Hi Sri Ram, good evening. Thank you, Rahat. All right. So I can mention over here very simply, magnetic monopoles don't exist. They are always in the form of dipoles. They are always in the form of dipoles. You cannot have just North Pole and South Pole separately. It is not possible. That is the reason why the field lines are always in closed loops. These are not possible. Is this absolutely clear, my dear warriors? Pakka? Everyone? Let me know. Okay. Okay. Maybe I'll tell you Ayapan on direct message. Okay. Not here. Alright. Okay. Now observe. If I want to now define what is magnetic field, remember the symbol was B, magnetic field symbol was B. How do I calculate magnetic field? Because electric field, I know I used to define it like this. Electric field used to be defined like this. E vector was the force acting per unit charge with the limit Q tends to 0. Now, if I want to define magnetic field, if I want to define magnetic field, if I go by the same logic, and I say, okay sir, magnetic field will be limit force acting on a magnetic charge, Qm is actually a magnetic charge which is North Pole or South Pole. Like a positive charge or a negative charge will have some coulombs of charge which creates electricity. So that quantity which creates magnetic field, I will call it magnetic charge, and magnetic charge is basically magnetic polarity, which is your North Pole and basically your South Pole. So understand there is a small difference in the symbol. So Q over here is charge, electric charge. This is electric charge in coulombs, but this Qm over here is a magnetic charge, and you will see the units later on, magnetic charge. And this magnetic charge also can be positive for North Pole and negative for basically South Pole, and limit this particular magnetic charge towards 0. So per unit polarity, what is the force will be magnetic field. But this definition is obviously wrong, because how can you get a single magnetic charge? If you get north, you will get south. If you take south, you will get north. So in mathematics, this looks good, but in practicality, it doesn't make sense, because physics does not allow even taking a single monopole. I just wrote it down here. Magnetic monopoles do not exist. They always exist as dipoles. So although this looks good in mathematics, this definition is not right in terms of physics. So this is definitely not valid. This is not valid, as Qm, which is a single monopole, which is a single monopole, can't exist. Can't exist. So this definition is definitely wrong. This is okay, guys. There is nothing wrong in this. Electric field we have been defining. So there needs to be a new way to define magnetic field. Alright. So there needs to be a new way to define magnetic field. So that's what we are going to focus on now. And that's what leads us to magnetic force. So till now, what have we studied? Different magnetic materials create a magnetic presence. They have magnetic properties which attract and repel each other. And these magnetic field lines have very similar properties like electric fields. Like the tangent drawn gives me the direction. They can't intersect. If they are parallel, they are uniform. If they are not parallel, then the field becomes strong or weak depending on the density. The only differentiating factor being they do not start or originate. They are closed loops, which led us to magnetic dipoles existence. Monopoles are never ever there. That's what we got. And that means we cannot even define magnetic field the way we defined electric field, because here we used to take a single charge, positive charge, but we cannot take a north pole or a south pole individually. So that leads us to the next concept, which is the concept of force on a moving charge. Now we know an electric charge, when placed in electric field, experiences electric force. So imagine this. If I take a electric charge and I put it inside an electric field, if this is electric field, then it experiences electric force. Then it experiences electric force. And this electric force, we already know that force is nothing but whatever that charge is multiplied by the electric field. Now just imagine if I take that same charge and this time I put it under the influence of gravitational field. Just imagine, gravitational field. Gravitational field. Neglect the mass. Gravitational field. Will a gravitational field apply a force because of its charge? Due to mass, yes, but due to charge, will it apply? The answer is obviously no. So there will be no force. There will be no force because of its charge. But yes, if it has mass, then that mass will experience force because of gravitational field. So understand, every field applies force on its own kind, or on a thing which it can relate to. Okay, so electric fields apply force on electric charges. Magnetic fields can apply force on magnetic polarities, basically north pole and south pole. Gravitational field can apply forces on masses. Masses themselves produce gravitational field, so they are its own kind. So now the real question is, can a charge which is placed, now placed instead of electric or gravitational field. Now imagine this is a magnetic field. This is a magnetic field. Now the question is, will this charge experience a force because of magnetic field? Remember, magnetism is a different thing, electricity is a different thing. So if you were living 200-300 years before, maybe you would have said no, but right now the answer is yes. And the reason I'll tell you, yes, there is a force. If you are wondering, is there a force? The answer is yes, there is a force acting on it. Even though it feels like, sir, this is electricity, this is magnetism, how can magnetism apply force on electrical charges? Aren't they of different nature? Like I said, before 200-300 years back, the answer would be no, but now the answer is yes. It's not that the physics changed, it's just that we discovered that electricity and magnetism are not two distinct things, they're actually the same thing. It's just a different perspective of viewing the same force in different ways. So that notion was given by Maxwell. Maxwell and Faraday actually made these concepts, and they made the world understand, listen bro, you thought electricity was different, you thought magnetic force was different, but actually they are not different. They are the same thing, you are looking at it from two different angles. It's like looking at the same window, one within the house and one outside the house. Inside the house, you are seeing the interior part of the window. From outside the house, you are seeing the exterior part of the window, but it is the same window. So the same logic applies to this particular concept. So electricity and magnetism are just two different perspectives of the same force, but they look, feel different because they were discovered in a different manner. After that, the whole scientific community got shook. They thought, oh my God, these two forces which we thought are different, they actually turned out to be the same. And that's when the topic came up, electromagnetism. Then people started thinking, maybe gravitational field is also very much similar to electricity or magnetism. Maybe we are looking at it in a different way. So everybody started looking at gravity and electricity and magnetism. Are they the same thing? Maybe we are looking at it from different angles. So this notion came of concept of unified force theory or unified field theory, where people thought maybe there is only one force in nature, but we are categorizing, classifying it in different ways because the manner in which we are observing or experiencing it. So people tried doing it, but till now we are not able to figure out if gravity and electromagnetism are actually the same force. So there is no such proof as of now, but maybe someday there will be. Maybe there is actually no similarity. But also people say gravity is not a force. That's a whole different discussion altogether. But you should know these things are there. So if you pursue physics, maybe in ISER or IISc, or maybe you take up engineering physics, these are the things which you might be interested to work on. Yeah, is that absolutely clear, guys? Do you understand this concept of how electricity and magnetism are actually the same concept, but of different from different perspectives, two sides of the same coin? Gravitational force for now is a completely different force altogether. So it cannot affect a charge. It can affect a mass, yes, not a charge. So now we are going to study how magnetic field affects a charge, which is an electrical thing, quantity in nature. Okay. Yes, it's a one shot, Sanjeevan. Yep. Yes, the lords, you can definitely get in. Yes, Josita man, I will, I was. Okay, very good. Amazing, amazing. So, a lot of experiments were conducted on these charges, and in the following cases there were no forces, only in certain cases there were forces. What were those cases? Let me explain. This charge is right now, is basically at rest. Then we take this particular charge and make it move. It is in motion, this same charge in motion. Then what was done is you take this particular magnetic field, make it pass through it, take this magnetic field. So this pink line is our magnetic field, guys. This is our magnetic field. Alright. In all these scenarios, it was found that there was no force acting on the charge. So when the charge is at rest, or when the motion of the charge is either parallel or anti-parallel to the field, in all these cases, no force was experienced. No force was experienced due to the magnetic fields in all these three scenarios. But the moment you take this particular charge and you send it into motion, let's say like this, with some velocity, and you place it inside the magnetic field, there is a magnetic field being generated by something else. Immediately it was found there was a force acting on it, and in this scenario it was found that the force came out in the inside direction. Yes, there was a force and it came out to be in the inside direction. Then they tried out all different sorts of things. They said, okay, what if I take up a negative charge? If I take up a negative charge and send it in the same direction, in that same magnetic field, then it was found the force also flipped in direction. Magnitude was same, just the direction flipped. The force came out to be towards the observer, basically out of the plane of the board. So this dot, remember, this are vector notations. So if I show a dot with a circle, it is basically out of the plane. But if I show a cross with a circle, it is inside the plane. So when I say out, that means it is towards you. It is towards you. But when I show in, it is away from you. It is away from you. Then they tried out all sorts of combinations. Then they said, okay, what if I take that same positive charge, but if I put it downwards, if I throw it downwards in the exact opposite direction in that same field. Then they saw that if velocity is reversed, then also the force got reversed. So again, the force came out. Again, the force came out in the exact opposite direction of this. Then they thought, what if I reverse the velocity and reverse the charge both? Well, if you take a exact opposite charge and even reverse its velocity and throw it in the same magnetic field, then it was seen that the force does not change. The force comes out to be exactly the same in the same direction. So that means the force direction does depend on the sign of the charge, and it also depends on how the velocity is. And this velocity has to be basically making some kind of an angle with the magnetic field. If there is any velocity which is parallel or anti-parallel to the magnetic field, or if it is not there only, then there is no force. So in all these cases, as you can see, there was force experience. So from this came a simple, concise relationship relating the force, charge, velocity and the magnetic field. So what does it look like? Let me show you. Say for example, you take up a charge, and let's say it is right now moving in some direction, and for now let me do one thing. This is your charge basically. This is your charge basically, and let's say it is now thrown like this in this plane. That white color is basically the plane of that charge, the plane of that plane in which that charge is there. And let's say at that location the magnetic field, let's say the location of the magnetic field is something like this. The magnetic field is something like this in that same plane. So you take a plane which contains both velocity and the magnetic field. Then it is found that the force on this charged particle happens to be perpendicular to this plane which contains velocity and the magnetic field, and it is something, let's say like this. It's something like this. This is that force. This force is perpendicular to the magnetic field also. It is also perpendicular to the velocity. There is definitely some kind of angle between the magnetic field and the velocity, which I am going to call it as theta. So this is the plane containing velocity and magnetic field. This force, magnitude wise, came out to be the value of the charge into the value of the speed into sine of the angle between the field and the velocity multiplied by the magnetic field value. So the magnitude of the force, that means the length of this vector, depends on how much is the velocity, how much is the magnitude of the charge, how much is the magnetic field, and how much is the sine theta between the field and the velocity. These are all experimental. But if you obviously want to find out the vector quantity of the force, as you can notice, there is sine theta, there is velocity, there is magnetic field as a vector. So obviously there will be cross product. Charge is a scalar quantity, so leave it out of that equation. I mean, it will be like a scalar multiple, nothing else. And here you will have V cross, instead of sine theta, you will put cross, and then you will just put magnetic field. So the force on a moving charged particle, is given by QV cross B. So this is nothing but the force on a moving charge in a magnetic field. Very, very important. Magnitude wise it will be QVB sine theta, but if you want to look at it in vector form, it will be QV cross B. QV cross B. So now if you go back to all these diagrams, it makes sense. Over here, velocity is on the top, magnetic field is on the right. If you take your right hand, point all the 4 fingers upwards and slowly rotate it towards the magnetic field, the thumb points in, which is the direction of the force. Here, even though V cross B is inside, this charge is negative. So because of that, when you multiply this vector with a negative sign, you will get a negative vector. That's why this inside vector flips and comes towards you outwards. So the negative sign of the charge is basically making this whole quantity negative. So the force reverses the direction and comes exactly opposite way. Here if you notice V cross B, velocity is down. So put your 4 fingers down and B is that way. So if you do V cross B, you will notice the thumb comes outwards towards you, which is exactly what I have shown. But if the same charge was negative, whatever is that direction will be flipped, because it will now make the entire quantity negative. So you will see the force going inwards. Is this now absolutely clear? In these situations, velocity itself was 0. So obviously 0 force. Here sine 0 is 0, sine 180 is 0. Remember, the magnitude is having sine theta over here. So if theta is 0 or 180 degrees, both the scenarios it will be 0. That's why there will be no force. So that is the reason why in this scenarios the force is 0 in spite of velocity being there. But in this scenario there is no force because speed itself is 0. Got it? So I have covered all the possible scenarios of all the possible signs of velocities and charges. So this formula becomes very, very important and critical. Alright? Amazing. Hi Donda Patvishal, welcome aboard. Yeah. When is the next live class? Usually my classes are on Fridays, man. Almost the same time. Okay. So now, how much, sir, is this magnitude of the force? Let's take a simple example so that you make sense out of it. Say you take an electron or a proton decently massed, whose mass is 10 to the power minus 27 kg. Oh, before that, we had to do one more thing. And what was that one more thing? Let me show you. This formula now helps me define magnetic field. I'll tell you how. Say for example, my velocity happens to be perpendicular to the magnetic field. That means my theta is 90 degree. So sine of 90 degrees will be 1. Therefore, my force which is there will be nothing but whatever is the charge into V into just B, because sine theta was 1. Now if you rearrange these things, you will notice therefore B will be equal to force divided by charge into velocity. Now in this scenario, please remember velocity was already perpendicular to the magnetic field. We already know force is measured in newtons. Charge we know is measured in coulombs. We have already defined what a charge is. When you take an ampere of current, pass it for 1 second, the amount of charge flown is 1 coulomb. We already know what a velocity's unit is. It is nothing but how many meters you are traveling per second. So since all these units are defined, naturally we can define magnetic field as, if you take a coulomb of charge and throw it with 1 meter per second perpendicular to the magnetic field, and the force happens to be 1 Newton, then that field which you are applying is 1 unit SI, and that 1 SI unit is called as a Tesla. So 1 Tesla unit of force is when you take a coulomb of charge and throw it with 1 meter per second perpendicular to the field, and it happens to experience a Newton of force. So that field which you have applied on that charge is a Tesla of field. So that is how you define the magnetic field, not like this, which I had shown here. So this does not come under the definition of magnetic field, because you cannot have a magnetic monopole. So this is how we define a magnetic field. Is this absolutely clear? There is another unit of magnetic field and it is called as a Gauss, and 1 Gauss of magnetic field is 10 to the power minus 4 Tesla. 10 to the power minus 4 Tesla. The short form of Tesla is T. Like for Newton it is N, meter it is M, second it is S, Coulomb it is capital C. So here it is capital T. So 1 Gauss is 10 to the power minus 4 Tesla. Now this Gauss is an independent unit and that conversion factor was done later on. How much is the typical magnetic fields of different objects? So for example, the Earth's magnetic field around the Earth is typically of the order of 10 to the power minus 4 Tesla. If you take a bar magnet, if you take your regular bar magnet, it is typically of the order of 10 to the power minus 2 Tesla. Now you can probably guess why this unit of Gauss came. It came from the Earth's magnetic field. So Earth's magnetic field is usually measured in Gausses, which is very small, 10 raised to negative 4 Teslas. So that's where that unit comes from. Anyways, a bar magnet is around, this looks like bar mag. Okay, let me put some decent space. Yeah, this is a bar magnet. Is around 100 times stronger than the Earth's magnetic field, 10 raised to minus 2 Tesla. If you have seen MRI, CT scan machines, those machines are of the order of 1 to 3 Teslas. And that field is so strong, my dear, it can literally suck out if there is some metallic body on you or within you. And it can literally be fatal. That's why when you go for a CT scan, MRI scan, whatever, they ask you, please take out all metallic objects from your body. If you are wearing a necklace, watch, whatever, remove it. If you are having a rod which is metallic, if you have some tooth which is metallic, you cannot go inside an MRI machine. If your tooth is metallic, imagine, that's it, the magnetic field of 1 to 3 Tesla is so strong, you can literally pull out that tooth. Okay, if you are wearing a chain, it's just going to cut off your neck, man. So that's why they don't allow these things inside those machines. So a Tesla of field is a strong field. So even 10 raised to minus 2 Teslas are so strong, which you have typically experienced with your regular bar magnets in loudspeakers, fridge magnets, other things. But you might have seen or heard about neutron stars. Neutron stars. Neutron stars. These stars are those stars which basically die out after their fuel gets exhausted. They are spinning at very high speeds and all of that. So even these dead stars, you will notice the fields are of the order of 10 raised to 5 to 10 raised to 7 Teslas. So just imagine the kind of strength this neutron stars have in terms of magnetic field. Just think about it. What would even happen if you take a metallic, basically a magnetic object near this neutron star? Immense force. Forget about gravitational force, even magnetic force will be so strong. I feel even a human body which has some magnetic properties, of course, we have hemoglobin inside our blood, and hemoglobin, hemo is nothing but iron. So that iron is slightly magnetic in nature. So definitely I feel even our blood will start feeling that force. So insane effects in such a neutron star. Is that absolutely clear, my dear warriors? Understood? Yep. So Gauss is a separate unit, like you had, what should I say, man? Centimeter is there. Centimeter is a SI unit, right? CGS unit, or you have foot as a separate unit. So same way, Gauss is a separate unit of measuring the magnetic field. That's all, nothing else. Is that now clear? Agrim Tiwari? Yeah, I'll be sharing the PDF, Rasi Kuju. Definitely. After the session is over, by tomorrow. Yeah. Yes, Satish, most of the Fridays my classes are there, unless there are some changes or some issues. So usually on Fridays or Saturdays, I will be taking the classes. Okay, cool? Great. So we have now defined what magnetic force is and how it acts on a moving charge QB cross B. You can use your right hand thumb rule to do the calculation. V cross B will give you the direction of the force. Yes, use your right hand thumb rule. If the charge is positive, if the charge is negative, exactly the opposite direction of the thumb. Okay, so that's very important. And then we also defined how magnetic field is in terms of force, charge and the perpendicular velocity, and that's how we defined a Tesla unit of magnetic field. Is that clear, guys? Now let's solve a question based on this. Example, if you take a proton whose typical mass is 10 to the power minus 27 kg and it is projected, and let's say it is projected at a decent speed of even, let's say, 100 meters per second. Actually, it is not that large. It can go at even much higher speeds. And at let's say 30 degrees to a field of a decent field, let's say we take 0.1 Tesla, find the force and acceleration. Find the force and the acceleration of that proton, of that particular proton. So let's start. We all know the magnitude of the force is given by charge into speed into sine of the angle and into the magnetic field. If you notice, the charge of a proton is 1.6 into 10 to the power minus 19. The speed is given to be 100. Sine of theta, guys, so it will be sine of 30 degrees multiplied by the magnetic field, in this case is 0.1. So that will make it, well. So this will be 1.6. Sine 30 is nothing but half. Minus 19 and plus 2 zeros will make it minus 17 into 0.1, which is a 10 power minus 1. So it will make it minus 18 again. So 10 to the power minus 18. So this will become nothing but 0.8 into 10 to the power minus 18, which is as good as saying 8 into 10 to the power minus 19 Newton. Obviously, the force is very small. Very small. Even though this field is quite strong, speed is decently strong or decently high, and angle is also okay, fine, 30 degrees. Even then the force is small. So you might be wondering, sir, why do we even study it then if the forces are so small? But the interesting part comes when you figure out what is the acceleration, and we all know acceleration by Newton's law is force divided by the mass. So the force is of the order of 8 into 10 to the power minus 19 Newtons. Mass is 10 to the power minus 27 kilos. So it will become 8 multiplied by minus 27 will become plus 27. So 27 minus 19, guys, that's going to be 8. So 10 to the power 8, this will be meters per second square. Is that right? So acceleration is very large, and that's what matters. The motion will be affected. So you can see, even though the force is small, the mass is even more small, and that's why acceleration is quite large, and that's the reason why we study it. Cool? Got it, everybody? Paka? Awesome. Now let's say I give you some typical cases and I ask you figure out what's the direction of the force in all these cases, just so that we are comfortable in finding the force, nothing else. Otherwise, at the end of the day, these are all simple right hand thumb rules. You take a charge, throw it like this. You take a charge, throw it like this. Charge velocity. You take a charge, make it come towards you. You take a charge, make it go away from you. You take a charge which is negative, and let's say it is going like this. You take a charge which is negative, and let's say it is going like this. This is negative charge. This is going like this. Okay. And in all these scenarios, let me show the magnetic fields. First scenario, magnetic field is like this. Next scenario, okay, over here the magnetic field is like this. Here the magnetic field is, let's say, like this. Here the magnetic field is inside. Here the magnetic field is let's say like this. Okay, so I'm just showing some random directions of magnetic fields here. Let's say the magnetic field is towards you. Okay, so in all these scenarios, I want to figure out what is the direction of the force. Just figure out what is the direction. What is the direction of the force due to the magnetic field on these moving charges. So let's try it out, everybody. So try to figure it out on your rough sheet. If you have a rough sheet for all these 6 scenarios, just try to figure it out. Just use your right hand thumb rule. In some scenarios, maybe the answer is 0. I don't know. All right, come on. Let's start with the first one, then second, then third, then fourth, then this fifth, and then this sixth. Come on. Let's start with the first one, guys. Let's start with the first one. Okay. Pranita, which part you want me to explain? Let me know. Yeah. And if you're new to the channel, make sure you're a part of the channel by subscribing and, mark your attendances so that you do not miss the next class. You do not miss any of the previous classes or these lectures might get lost. And there are a lot of other things apart from these lectures which I give you. A lot of content, a lot of information, a lot of strategies, a lot of important news, everything. So make sure you're a part of the channel if you're not done that yet. Okay. So first scenario, let's start. In this scenario, if you do velocity cross B, first of all, charge is positive, so don't have to worry about flipping any of these vectors. So V is here. Slowly turn your right hand fingers like this. Hold your right hand in the direction of velocity, turn it towards B. You will see the thumb comes towards you. So 100% the force is towards you. Force is towards you. In this scenario, V is upwards, velocity is upwards. Velocity is upwards. And magnetic field, you can see dot with a circle, that means it is towards you. So now you need to be careful. So if I am a student watching this lecture, I will take my right hand on the left side. I'll take my right hand on the left side. I'm making you visualize from your perspective. Hold your 4 fingers on the top. Hold your 4 fingers on the top and slowly, because that's the velocity direction, and slowly make it come like this. It should point behind you because that's how the magnetic field is going. It's coming from here and going like this. So make that hands, fingers go like this, V cross B. You will see the thumb going this way. So that means the force is directed in this direction. The force is directed in this direction. Can you see that? So V is up, B is towards you. So V cross B makes the thumb goes like this. What about this scenario? V is towards you, magnetic field is right side. So if I'm a student watching this class, I will take my right hand, keep it on the right side, but I'll have to take it little behind because my velocity is coming like this out of the plane of the board. It's coming from front and going behind me. So V is there. Magnetic field is towards my right side. So V is this way, B is this way. So if I do V cross B, the thumb goes up. So naturally, the force will be directed in this direction. Are you able to see that, everybody? Let's go to the next one. V cross B. Oh my God, guys, V is inside, B is outside. They are literally anti-parallel. So sine 180 is 0. So the force will be 0 because sine of 180 degrees is 0. How is it 180? You might not be able to sense it here, but actually the velocity is going inside. Magnetic field is coming outside. So if you look at it sideways, you will realize they are actually anti-parallel, meaning the angle is 180 degrees. So hence answer is 0, no force. What about this scenario? V is up, B is here, V cross B comes towards you, but don't forget it's a negative charge. So exactly opposite. So that's why the force will come inwards. The force will come inwards. See if you are able to get it. Okay. All right. Pankaj, I cannot help you in that, man. This is English channel. First of all, this is not even an English channel. Okay. Next, here, as you can see, V is here, B is inside. So look at it, how I'm holding my right hand. My right hand, I'm shifting it towards the left side. I'm taking the right hand, shifting it towards the left side. V is this way, and I'm slowly bending my fingers inside because B is inside, magnetic field is inside. So V cross B, the thumb goes down, but it's a negative charge, so I have to flip it. It's a negative charge, so I have to flip it. V cross B, thumb goes down, but negative charge, so that's why I will flip it. So this is the direction of the force. So with some practice, I believe you will be able to definitely use your right hands properly and get these directions. So I have taken some literally worse directions. Most of the times the directions are simple, but still you should know how to calculate the force in any scenario, no matter where the velocity is, where the field is, no matter how the force is. Okay, so you should be able to twist your hand. That's also a little bit of hand exercise, wrist exercise. That's what you need to do. Cool, guys? Everyone understood till this point? Amazing. Great. Now that we have understood what this force is and how to calculate the force, the magnitude or the direction, let's take some scenarios. First, we know that if you keep the charge at rest or if the magnetic field is parallel or anti-parallel, then there is no force. So, first scenario I am taking, if you take a charged particle at rest, no matter how strong the magnetic field is, it really doesn't matter that this particular charged particle at rest stays at rest. Reason being, the force acting on it is 0. Since the force acting on it is 0. Also, if I take a charged particle having some velocity, the charge which moves along, now that along can be parallel or anti-parallel both, along the magnetic field. So the magnetic field can be either parallel or anti-parallel, doesn't matter. That also experiences no force. It experiences no force. So what will happen? Because even this, the force is 0. Because the force is 0, can I also say acceleration is 0? And when acceleration is 0, the velocity will remain constant. So charge moves along the field with uniform velocity. Meaning the path taken by the charged particle will be a very nice straight line. So it moves along a straight line. Alright, it moves along a straight line with constant velocity. There is no change in the velocity. It just keeps moving. There is no change because there is no force, no acceleration. So velocity, direction wise as well as magnitude wise, will be constant. But now what will happen if the charge is thrown at an angle? And that is what we are going to study. So the first scenario, let's make the charge move perpendicular to the magnetic field. So let's say our magnetic field is inside for now. This is your magnetic field. And our charged particle is now thrown, say for example, like this. This is our charged particle, which is thrown like this, perpendicular to the magnetic field. How is it perpendicular? It might not be very easily apparent over here. Velocity is like this, magnetic field is inside. So magnetic field is inside, velocity is like that. So visualize it, it is actually perpendicular to each other. Okay, so you have to visualize it from the top view. Magnetic field is inside, velocity is this way. So yes, they are perpendicular to each other. Such a scenario is called as a transverse field. Transverse field. Transverse means perpendicular. So meaning the velocity is perpendicular to the magnetic field. And because this happens, I can also quickly say theta will be 90 degrees. Theta will be 90 degrees. That means sine of 90 will be 1. Sine of 90 degrees will be 1. So when I try to calculate the force acting on it magnitude wise, it will be charge into velocity into magnetic field. That's it. There is no sine theta in it because sine theta itself is 1. QVB. Simple. Correct? There is no sine quantity in it. Now, what is the direction of the force? Can you visualize and tell me? Everybody spam the answer in the chat box. Is it up, left, right, in, out? Where is it? Come on. Yes, smile, silence. This is more than enough for your JEE, man. This is your foundation concepts proper from basics to JEE level. And after this, obviously, once we have done most of the things, then we will do with the problem solving sessions, then revision, mock tests, JEE Advanced, JEE Mains, all kinds of things. But first, concepts, applications, understanding, theory and visualization. All of this is what we need. Come on. What do you think will be the direction? Well, take your right hand, everybody, point it in the direction of velocity. Magnetic field is inside. Turn, curl your fingers of right hand, 4 fingers. The force will come exactly upwards. So yes, the force will be exactly like this. That's how my force will be. Is that right? This is how the force vector will be. Now, once you realize the force is perpendicular to the velocity and magnitude wise it is not even changing, because Q is not changing, V is not changing, B is not changing. Why is speed not changing? You might be wondering, isn't it? Sir, how come speed will not change? Speed should change. A lot of people have, sir, force is there, acceleration is there, so speed will change. Very true. That is what your thought process is initially. But I'll tell you what. Look at this scenario. Force is perpendicular to the velocity. That means, can this force do any kind of work? Can this force do any kind of work? Always, see, velocity and magnetic field can have any angle, that's okay. But force, it is a vector product. And the vector product is always perpendicular to the individual vectors. So, force is perpendicular to the velocity vector. That means there is no work done. There is no work by this magnetic force. And there is no work by this magnetic force. By work kinetic energy theorem, it can't change the kinetic energy. So, no change in the kinetic energy, and kinetic energy depends on the speed. So, there is no change in speed. No change in the speed. That means final conclusion is this force can only affect the direction. Yes, the direction it can change, but can't change the speed. This is a very, very important line, very, very important concept. In JEE Advanced, so many type of questions are dependent on this. So, it can't change the speed, but what it can do is only affect the direction. Is this logic very, very clear, my dear warriors? The force is perpendicular to the displacement. So, work done is 0, work is 0. So, no changes in the kinetic energy due to this force. Other forces can, not this one. So, speed can't change, but obviously this force will do something and it can only change the direction. That means that in this particular scenario, my speed is not changing, charge is constant, field is constant, this is uniform. So, force is also constant. The only thing it can do is change the direction. And what kind of motion happens when your force is constant, speed is constant, force is perpendicular to speed or velocity, and only direction is changing? Can you recollect? Is there some kind of motion which exactly follows all these criteria? Class 11th also? Well, then class 11 students should spam in the comments, not just in the live chat. After the session is over, sir, class 11, Shreyas Sir, come, sir, team, come, fast. More comments. Only then it will happen, man. Yeah. Think about it. Force is constant, magnitude wise. Speed is constant. Force is perpendicular to the velocity. Also, direction is changing. Speed is not changing. There is one thing. 11th standard you have learned this. Circular motion, that too uniform. In a uniform circular motion, the speed is always constant. Constant speed it will go. Force is centripetal. The force keeps changing the direction but is always constant, mv square bar, mv square bar. And the force is perpendicular to the velocity. It changes the direction only without affecting the speed. So that's it. So the only possible outcome of this scenario is it should go in a circular path. Something like this. This will be, example, the center. And yep, there will be some radius like this, you can say. This is the radius of that circle. And what it is now doing is a uniform circular motion. That's the only possible way. Uniform circular motion. Is that absolutely clear? Why? Yeah? Everyone? All right. Amazing, amazing. Fahad, don't waste our time by coming to English channel and just spamming. I know you have other channels by the language you are speaking. You can go there and spam, not on the English channel over here. Okay? So don't waste our time by asking stupid questions if it is live and recorded. What nonsense question is this? If it is live, you can see it is live. It is live. Simple. So if this is a uniform circular motion, we can use the concepts of uniform circular motion to find the time period and to find out even the radius of the circular path. How, sir? Well, we all know by Newton's laws of motion, this force is going to be mass into acceleration. Basically, it is acting like the centripetal force. Centripetal force. So this force is nothing but Q into V into B, and the acceleration is centripetal acceleration. That means it will be V square divided by R. One of the V's will get cancelled. So charge into the magnetic field will be mass into velocity divided by R. I want to, let's say, find out the radius. So I will take R on the top. Mass and velocity are as it is over here. Charge and field, I will shift it below. So it will be charge into field. Some people also like to put it as mass into velocity is nothing but the momentum and divided by charge into field. We also know momentum by 11th standard formulas is root of 2 times of kinetic energy, 2 mk. So root of 2 times mass times kinetic energy, and this divided by qb. All these are equivalent, guys. So let me just mention it very clearly over here. So the momentum P is nothing but mass into velocity. Kinetic energy formula K is nothing but half mv square, which is also P square divided by 2m. You might have seen this. That is why if you shift 2m here, 2mk under the root becomes the momentum. That is what I have written over here. All this you have studied in your 11th standard. So this is 11th standard syllabus. There is nothing about 12. So same thing I have used here. So all these are equivalent, but the only formula for now which you should know is this. R is mv by qb. mv is momentum. That is very natural. And momentum is root 2 mk. That is also easily derivable by using 11th standard concepts. So I just mention it because in some questions they will give you kinetic energy, or they will ask you about momentum ratio or something like that. So that's when you will transform it into those forms. But otherwise, this is more than enough. Once I know the radius, I can easily figure out what is the time period also. What is the time period? What is the time period of this uniform circular motion? How do I figure it out? See, the time period of revolution, it is revolving in circular path. So the time period, time is distance by speed. So it will be nothing but how much is the circumference divided by the speed. Time is distance by speed. So time period of revolution is distance by speed. So what do we do? Circumference is 2 pi r. Speed is nothing but v. Okay. But what is R? We just figured it out. mv divided by qb, mass into speed divided by charge into magnetic field. So I'll just put mass into speed divided by charge into field. V and V is getting cancelled. So I will get this as 2 pi m divided by charge into field. This is the formula for time period. So let me just block it. You have to remember, guys, because direct questions will come. And interesting thing, it is independent of the speed. Independent of velocity. No matter how fast you throw it, the time to complete a circle is still the same. You throw it slowly, still the same. You throw it fast, still the same time. But yes, the radius depends on the speed. You throw it slowly, the radius is small. You throw it very fast, the radius is big. It goes in a big circle. But even the small or the big circle will complete it in the same time period. That is awesome, guys. That is crazy. So one way to visualize it is, if you take a positive charge, throw it with low speed, and you take same positive charge and throw it with a very large speed, you will see one of those positive charges will go in a small circle, other one will go in a much bigger circle, maybe like this, but both of them will complete their journey in the same time. This will take same time. If you take an equal amount of negative charge of the same mass, that's very important. Speed doesn't matter. Because there's a negative charge, you will notice the negative charge will go exactly the opposite way. So the negative charge will go exactly the opposite way, somewhere like this, in this side. But yes, it will be still a uniform circular motion, but on this side. So no matter what the speeds are, times will be the same. All of these will take the same times. Here remember, all these charges are same in magnitude. Maybe the signs are sometimes different. Speeds are different. This could be V1, this could be V2, this could be V3. Doesn't matter. No matter what the speeds are, times are the same. Radius are different because speeds are different. Is that clear? So this is a very interesting diagram. How magnitude of the charge and only matters and the mass matters, nothing else. Clear, right? Okay. So to summarize, a charged particle thrown perpendicular is going to perform uniform circular motion. The centripetal force is provided by the magnetic force. Radius is mv by qb. Time period is 2 pi m by qb. Time period is 2 pi m divided by qb. Now, let me show you some examples on this. Okay, and then we will proceed ahead. Say for example, you have been asked an electron whose mass is 10 to the power minus 30 kilos approximately is projected in a transverse field, of 10 Teslas, which is very huge, okay, at, or let's say, okay, 10 Teslas only will take, at 4 meters, or let's say 400 meters per second. Find the frequency of revolution. Find the frequency of revolution. Also, what is the radius? Let's estimate how small, big these values are. Let's start with the radius first. It's easy to calculate. Radius is mv divided by charge into the magnetic field. Mass is given to be of the order of minus 30 kilos. Speed is 400. Charge of an electron magnitude wise 1.6 10 to the power minus 19. Magnetic field is 10 Teslas. One of the zeros got cancelled. This 0, if I swallow it here, it will become minus 29. 4 will remain. These zeros have got cancelled. 1 0 I have swallowed here. This number of 1.6, I can write it as 16 and I can then put it as minus 20. No harm in doing that. 4 will go with 16 4 times. Minus 25, take it on the top, it will become plus 20. Plus 20 minus 29 will make it 10 raised to minus 9. 1 by 4 is nothing but is that right? Yeah. Okay. This is nothing but 0.25 into 10 to the power minus 9 meters, which is 0.25 nanometer. That's the radius. Very, very small size of the atom. So that electron is going, it's like within the atom, it's revolving. Very, very small radius. Okay. Next, what might be the frequency? So for frequency, we use the formula 1 by time period. Time period is 2 pi m divided by charge into the magnetic field. Let's start substituting everything. So therefore, the frequency will be charge is 1.6 10 to the power minus 19. Magnetic field is 10 Teslas. 2 is 2 only. Pi is 3.14. And the mass is 10 to the power, how much is it? Minus 30 kilos. So let's see what do we really get. So this will become 16. 10 and 1.6 will cancel the decimal into 10 to the power minus 19. Then over here 2 into 3.14 I can write it as 6.28. Minus 30 will go on the top, will become plus 30 as it is. Now 16 by 6.28 guys, we can just do the math. I will use the calculator just to get a very good estimate, or else we can get an approximate. We close to 3. So this is 16 divided by 6.28 comes out as 2.54. Okay. So this will be 2.54 and this will be minus 19 plus 30 means it will be 10 raised to how much? 11? 10 raised to 11. These many hertz. Frequency, remember, is in hertz, so that's the answer. Yeah. So it's extremely fast. This many hertz means these many revolutions every second, and the radius is also very, very small. That's what you can see. Cool. Now, this concept is exactly what is used in a device called as a cyclotron. You should just have an idea of it, although cyclotron is not there in the syllabus. Sometimes it just indirectly mention about cyclotron. So you should have an idea about it. Okay. So don't go exactly by the syllabus. This cyclotron is a device which is used to accelerate a charged particle. And to do that, there are two concepts which are mainly used. First concept which is used is exactly of this, where you throw a charged particle in a perpendicular magnetic field, it starts revolving in some radius and it has some frequency of rotation. That frequency or the time period, like I told you before, is independent of the speed. Same time, independent of the speed. No matter how large that radius becomes, the speed remains the same. The time period remains the same. Basically, frequency remains the same. So frequency is not affected by this value, if you notice, whatever this 400 is, because nowhere in the calculation that number 400 came. Now, the second concept used is the concept of acceleration due to voltage difference. If you take a charged particle and there is a voltage difference, what happens? That charged particle accelerates. So it goes from high to low potential, and that change in the potential energy converts into kinetic energy increase. So that increase of the kinetic energy basically increases the speed. So what happens is, we are going to use two concepts. One is revolution, uniform circular motion due to magnetic field. Second concept, acceleration due to electrical potential difference. So how does this lead to increasing the speed of the charged particle? One might say, sir, can't you just take two plates, one high potential, one low potential, and just accelerate it? Yeah, you could do that. But the plates, if they are very close to each other, the acceleration that you will get will be very less. And if the plates are very far, then the fields will just spread out everywhere, then the field will not be so strong, you cannot achieve such a great acceleration. And when the plates are very far away, to let it accelerate for a long time, a lot of undesirable effects might happen. The charged particle might go somewhere, air molecules are there, it will ionize it, so many random things. Instead, what we do, in a confined space only, in a small region, you can achieve all of these things. How? Look at it. There are two D's of a cyclotron, D's, because it looks like a, oops, what is this? It looks like a D, right? So these are the D's of a cyclotron. This is ulta D, opposite D, this is your regular D. These D's are like those plates, one at high, one at low voltage. So imagine you have a conductor at a potential and another conductor at another potential, so there is a potential difference. So if you leave a charge from one potential to another potential, high to low, so that decrease in the energy, potential energy, causes increase in the kinetic energy and increase in the speed. So going from higher to lower potential difference, the charged particle will accelerate. Got it? Everybody? The charged particle will accelerate. Now instead of the plate, it's a D, hollow D. Think of it like a hollow plate. I mean, think of two plates sandwiched, but in that space between those two plates, there is empty region. And this entire space is at one potential, this entire space is at one potential. Why are they not touching? Because I want potential difference. If they touch, that's it, gone, the potential difference vanishes. So I want one to be at a different potential than the other. Conductors should not touch, else potential difference will vanish. So a charged particle sent from here to here will accelerate. Got it? But now that acceleration happens for a very small time, because from here to here the gap between these D's is negligible or small. So then you are like, sir, what is the purpose then? We did not achieve great increase in the speed. So what we do, we again make that charge travel from one side to the other side by again increasing the potential difference. So sir, are you keep on going to increase the voltage difference? No, no, no. Instead what we do, we flip the potentials. We flip the potentials. Once a charge comes from here to here, we will make this as low potential and this as high potential. So when the charge comes from this side to this side, again it is going from high potential to low potential. Potential energy decreases, kinetic energy climbs up, speed also increases. When it reaches here, again I will make that charge come from here to here, high to low potential. That means speed will increase again. When it reaches here, again I will make it go that side. So whenever the charge goes from one D to the other D, I will reverse the polarities of these D's. That is why you see a alternating current source, AC source. Making sense? So the alternating current flips the polarities frequently at a regular time interval. So the charge is here, duck, flip, again accelerate. The charge goes here, flip, again accelerate. Charge comes here, again flip. So it keeps on accelerating. But then you might be wondering, sir, I don't think that will cause an increase, because if a charge goes from here to here and if you just reverse the polarities, won't it again stop and again go like that? That is why you need the magnetic field now. You don't let the charge go in a straight line, rather make it go in a circular path. So initially you leave the charge with a very small speed. The magnetic field is perpendicular. And because the magnetic field is perpendicular, the charge will go in a uniform circular path. So now the charge is going like this, like this, like this with a uniform speed. The moment it reaches here, I heard the arrow marks are wrong actually, ignore. So the moment it reaches here, there is a voltage difference, there will be an increase in speed. By the time it reaches here, you reverse the polarities of those D's. Now what will happen is, slowly the charged particle will go with a uniform speed. No change at all, because the potential is constant inside. Once it reaches here, again the speed will increase. And now again you flip the directions of the polarities, but inside a D the speed is constant. When it reaches here, again the speed will increase. So every time it reaches the gap, the speed increases. Within the D, the speed remains constant. And why is it remaining constant? Because magnetic field can't change speed. Number two, inside the D the potential is constant. Only outside or in between those D's there is a voltage gap. which causes that acceleration. So successive flippings of those polarities, and every half of a revolution you are increasing the speed consecutively, and when the speed increases, the radius also increases gradually, and slowly the radius keeps on increasing. When you have acquired the desired speed, then you let it go or fly off, or you turn off the magnetic field, so it will come out of that cyclotron with a very high speed. That is the concept of a cyclotron. Is this understood? Yeah. You can see the, say that the Ds act like a Faraday's cage because they are shielding the charge inside of it. Yep. At the end of the day, it's completely covered. A very small gap is there. It acts more or less like a Faraday's cage with equipotential surfaces. Only between them there is a voltage. So a low energy ion is accelerated between the Ds successively by alternating current, and within the Ds the charged particles are just turned around, maintaining their speeds, and then you slowly increase. And the best part about cyclotron, you don't have to worry, sir, if the speed increases, won't it take different time? Won't it take different time to come from here to here versus here to here? No. It will take the same time because time period is independent of the speed. So the AC source will always be of the same frequency. It's not like as it comes out, you have to change the frequency. No, don't have to worry. The time is the same. So that is helping us keeping the process simple. Else it would be a complex process if by chance the speeds would affect the time period. Luckily, it didn't. So AC is a constant frequency. Is that clear, everyone? 10 time, very good. Amazing, amazing, amazing. Satish understood, Zexist understood, Maulik, Kishore, Varis, Srini, Pankaj, everyone. Thanvi, Shruti, Sagar, clear. Hi VDST. Amazing, amazing, man. Now let's take another example of this scenario and let's see whether you can solve it. Say there is a charged particle thrown with some speed, it has some mass, and there is a particular region in which there is magnetic field which is uniformly present. That magnetic field is there inside and it is given to be uniform, and it is only there in this particular region of length L. Only there in this particular region of length L, nothing else. Now there are multiple questions on this. First question is, what is the minimum value of L so that the charge doesn't cross over the field region, doesn't cross over that field which is there. That means this charge particle which is going, it shouldn't go onto this side. So I feel there is a requirement of L, it should be large enough, else I feel it might go that side. Okay, that is the first question. Second question, if L is more than that whatever quantity is, whatever you have found, then how much time does it spend inside the field, inside that magnetic field? How much time does it spend? The third question which I am interested is, if this length is made exactly half of the minimum length, you require some length, but what you do is make it half, then obviously it is going to cross over to the other side. Then find the deflection in the path of the charge as it crosses to the other side, as it crosses to the other side of the field. Crosses to the other side of the field. These are the three questions, guys. That's what we are going to solve. Okay. So look at the scenario first. These questions can be more also. You can make many more questions. It can be a proper advanced passage, whatever you want to call it. Okay. So this is a proper good question. What is the formula for cyclotron? Well, cyclotron formula is exactly this, man. This is cyclotron frequency. Whatever I did, the same question can be asked. There is an electron which is projected inside a cyclotron. Find the cyclotron frequency. There is no change in the solution. This is exactly the cyclotron frequency because look at it. The moment the charged particle goes inside, you are flipping the polarities. Again, when it goes to the first D, you are again flipping it. So one cycle gets completed in one complete revolution. So the cyclotron frequency is exactly the regular frequency what you get. So the frequency of cyclotron is exactly the frequency what you would expect for a motion of a charged particle. That means it will be 2 pi m by QB inverse. That's it. Exactly the same formula. There is no change. Okay. So that's what I said. Chumma they will use that word cyclotron and you will think, sir, I don't know cyclotron. Nothing, man. Same formula is there. That's all. Okay. Cool. Now let's start solving these questions, guys. First, let's visualize why that length should be bare minimum so that it does not cross over. What would happen otherwise? Let's think. See, the moment that particular charged particle enters over here, things will change. The moment that particular charged particle is going to enter this particular region, what will happen? There will be a force on it. And what will be the direction of the force? See, if the magnetic field is this way, if the velocity is like this, if you do V cross B, immediately you will notice V is there, B is here. So force will be on the top. So the force will be like this. And that will cause the particle to go in a circular path. Now if this length is good enough, what will happen is, you will see length is wide enough, you will probably see it will go within that region and it will properly go like this, and once it reaches here, it will just come out like this. If the length is not good enough, then while it is turning, it might not be able to turn completely, so it will just go off to the other side. It will just go off to the other side. So the length is good enough, it will make a perfect U-turn. If the length is not good enough, while it is turning, because the length is not enough, so it will not be able to complete the circle, and that's it. It will just go to the other side. So when it is just bare minimum so that it is able to make that perfect U-turn, so it will look somewhat like this. Just it is able to complete its U-turn, and now it is going to return exactly, obviously, with the same speed. So it has made a semicircular path over here inside this field region. In such a scenario, this is a critical scenario, this length will be obviously L minimum. Are you understanding, visualizing this scenario? So now you can immediately guess, because this is doing a semicircular path, and this semicircular path is exactly that critical scenario, In such a scenario, obviously this radius of this semicircle, this radius of this particular semicircle will exactly match the width of this magnetic field region. So the radius will be L minimum. Therefore, L minimum will be just the radius formula, which is nothing but mass into speed divided by charge into magnetic field. Got it, everyone? Very straightforward. So we got the first answer very, very easily. So we found out the first answer. Great. Now the second question. If L is more, if L length is wide enough, then how much time does it spend inside the field? Okay, let's visualize that also. Let's say this L is larger. Let's say this particular L is larger than the L minimum. So this L is more than L minimum. What will happen in that case? Obviously, it will get a lot of time to spend inside. So as this charged particle will come, it will probably make a U-turn very quickly. It won't even reach the end. And once it reaches here, it is just going to come out like this. How much time will it spend? Exactly the time taken to complete the semicircle. So the time which it spends will be the total time period by 2. Because this is for a semicircle. Keep that in mind. Whereas this is for a complete revolution. Complete revolution. So the total time period we all know is 2 pi m divided by charge into the magnetic field. So therefore 2 will cancel and we'll just get pi m divided by charge into field. That is the time that it is going to spend. Clear? Alright. So it's wide enough so it can easily make that turn. So that was our second question which was asked. Now the third question. L is L minimum by 2. Then how much is the deflection? Because if it is less, then obviously it will go to the other side. But I think it will deflect. Alright. So let's visualize that as well. So it comes straight and now it's going to deflect. And from here, it will just continue going like this. So it has definitely deflected. If you notice, there is a radius to this circular arc. And that radius, I'll just leave it over here as it is. Speed will be obviously the same. That speed will not change. There is a deflection which has undergone theta. Whatever theta the radius has rotated by, exactly velocity also has rotated by the same angle. So the deflection of the path which you want to find is exactly this theta. So velocity was here, now it has turned here, that is the deflection. That is also the rotation or deflection in the radius of this circular path. So if I can find theta, my job is done. Okay. How do I find that out? First, let me mark this. This width is not just any random length. It is actually L minimum divided by 2. That is what the third scenario says. L is L minimum by 2. It's half of that minimum required length. You made that width shorter. That's why it was not able to complete the complete path. Okay, fair enough. How do I get it? Do I somehow know this radius? I think I know that radius. We had figured it out. That radius was actually L minimum. Do you remember? We had figured that out. That radius is actually L minimum. That won't change. L minimum. Since R is still mv by qb. Okay. Now maybe we can do a simple geometrical construction like this. This is that radius. This is also that radius. How about dropping a perpendicular over here? Dropping a perpendicular over here. Observe like this. Now this base of that right angled triangle is L minimum by 2. This hypotenuse of that right angle, which is the radius, is L minimum. This is that angle which I want. This was that perpendicular, correct? Now can you see, can we find out theta? Yes, sine theta. So let's do sine theta, guys. So sine of theta is opposite side, which is L minimum by 2 divided by L minimum, which is the hypotenuse. L minimum cancels, so it will be half. So that means my theta value, will be nothing but 30 degrees. So it will deflect exactly by 30 degrees. So all three questions done. So initially it feels like a very lengthy kind of a question, but it is not. Once you involve yourself, visualize what is exactly happening, you get the feel. Oh, this width is large enough, then it will immediately go back. If it is short enough, then it will go this side. If it is just enough, it will just barely touch on the other side and it will make a perfect U-turn. Understood? Hi VDST, welcome. Lakshya MHT CT student. Oh, nice. Okay, great. All right. Yeah. How spiral path get energy? Satish, like I mentioned, it's not the spiral path which is getting energy. Why that path is spiral? Because once it goes from here to here, at this point, the speed increases. So once the speed increases, it can't continue in the same radius. So that's why the radius will increase. Once it reaches here, the speed will increase. So it can't continue in the same radius. So it will go in a bigger radius. That's why the path is spiral. And why is the speed increasing? Because there is voltage difference between the disks. Why is it circular? Because there is magnetic field in this region and this region. There is a magnet which is kept, and that creates that perpendicular field which makes it go in a circular path. Is that understood? So spiral path is just to contain it in a small space, nothing else. And the circle's radius is gradually increasing because speed is increasing because of acceleration. Otherwise, magnetic field is not responsible for increasing the speed. It can't even change the speed, first of all. Got it? Yeah. So that is that particular question. Let's solve some questions, my dear. Okay. So this is one of the questions. A particle of charge q mass m is projected with a speed in a region of uniform magnetic field. The time period of the resulting circular motion is independent of. Well, time period formula, my dear warriors. Come on, everybody spam the answer. I'm glad, Satish, you understood this concept. Yeah. Any doubt, guys, like this, please make sure that you clear it off. I'm here to help you out on it. Okay. So I want all your concepts to be pakka, super duper. It should be in your head because you are going to solve JEE advanced questions also in the end, right? That is your end goal. So concepts should be pakka, full deep. You should understand thoroughly. There should be no confusion in your head. The moment there is confusion, the concept is not clear. You have to be firm in your foundations. So these basic classes, foundations to JEE, that is what is required. Okay. So time period, my dear warriors, time period is nothing but 2 pi m divided by qb. That was the formula. Mass is there, q is there, b is there. What is not there is velocity. So hence the answer is velocity. Got it, everyone? So speed independent. In fact, that's what I had mentioned also sometime back over here. So no matter what the speed, the time periods are the same. Okay, so that was the concept. All right, this was actually asked as a PYQ. Next question. A proton and an alpha particle are entering a uniform magnetic field with the same kinetic energy. The ratio of the radii of their circular paths. A proton, which is a positive E charge, alpha particle, 2 E charge positive, mass is 4 times that of a proton, because alpha particle basically will have 2 protons and 2 neutrons. So proton and neutron roughly are the same mass. So that is why I said alpha particle has 4 times the mass of a proton. Anyways, the ratio of the radii is how much? Whenever such ratio questions come, try to figure out the proportionality relationship. Who is dependent on whom and how? That's what you need to find out first. We all know radius is mass times velocity divided by q into b. But if you remember carefully, I told you mv is momentum and momentum is root 2 mk. We need these modifications sometimes in some questions, and this is such question. Kinetic energy is mentioned, so immediately you should realize we need to rearrange this or manipulate it in the form of kinetic energy. So going back to the equation, if you notice, where is it? Yep. Radius was root 2 mk by qb using the 11th standard knowledge. Root 2 mk divided by charge into magnetic field. So I can immediately say this is the root of 2 times mass times kinetic energy by charge into the field. That is the radius. Clearly mentioned, exact same kinetic energy. 2 is the constant, magnetic field is the same field it is thrown into. What is different is mass and charge. So that means my radius is related to directly root of mass and inversely to the charge. Rest all numbers are constants. Once you get this proportionality relationship, solving the problem is a piece of cake, guys. How? Observe. If I want to find the ratio of the proton upon ratio of alpha, because I know radius is proportional to root of m, so it will be proportional to mass of the proton upon mass of alpha particle under the root, and it is inversely proportional to the charge. So charge of the proton will come here, charge of alpha particle will go on this side. Now what about these mass ratios? Alpha particle is 4 times heavier than a proton, right? So this will be 4 times as compared to this. Alpha has 2 times positive charge as compared to a proton. Proton is a single E, alpha is a double E. So that means this will be 2, this will be 1. Now this obviously becomes 1 by 2, this will become 2 by 1, 2 cancels. So hence 1:1 ratio, which means option B is the right answer. Is that clear, guys? Understood? Yeah? Very good. Sir, we are eagerly waiting. Yeah, sure, Cosmic. Definitely, man. I know a lot of you are facing a lot of difficulties in planning your schedules, planning your roadmaps, planning your timetables. A lot of you face difficulties managing your boards with competitive exam. I know a lot of you keep asking, searching for the strategy videos. I will help you out with that. Don't worry. Okay. So Shreyas Sir is going to, help you out in planning in a personal way. All right. Don't worry. Yeah. Because everybody's timetables are different. Everybody's roadmaps are different. Everybody's starting points are different. Everybody's school timings, coaching timings, everything's are different, guys. So that's what we are going to, do in the next coming 2 days. Don't worry. All right. Cool. Yes. 1:1, 1:1, 1:1. Good night, Sakal. What happened so fast? Ayo. All the best, man. Next, electron, proton, alpha enter a region of magnetic field with same energy. Well, what is the relation between the radius? Who is more, who is less? Are they equal? That's the question. We just figured it out. Kinetic energy relationship √2 mk divided by charge into field. Field is same, 2 is constant, kinetic energy is same. So R is proportional to root of m by q. So now if I do this, radius of electron is 2, radius of proton is 2, radius of alpha particle, if I take 3 numbers ratio. So for electron, the mass is going to be forget that first. Think like this. For electron, the mass is going to be very less. Charge is same as that of the proton. So if you just compare electron and proton, it's actually very easy. So between the electron and the proton, the charge is same. The mass of the electron is much smaller than the mass of the proton. So denominator is same, numerator is different. So radius of the electron is definitely going to be lesser than radius of the proton. Is that right? Great. If you compare now proton and your alpha particle, we have solved that question before. We have just solved that question before. If you see the previous question, the answer was 1:1. Yes, for a proton and a alpha particle. We just saw from the previous question, the radius of the proton is the radius of the alpha particle. Check the previous question. That means I now know what is the relationship. Radius of the electron will be less, proton and alpha will be equal, so the answer will be option A. Understood, guys? So using the previous knowledge plus this new thing, because mass of the electron is very less, charge will be same magnitude wise, so radius of electron will be very less actually. Got it? Option A. Correct. Yes, Cosmic. Perfecto. Moving on to the next question, guys. Here it is. There is a particle. This is a good question. There is a particle of mass m and charge q which enters a sharp bounded region of magnetic field at some angle theta relative to the normal of the boundary line. Okay, we'll visualize it. First, let's read. The particle turns inside the field and emerges back out of the field free region. The total time spent inside the field is how much? This same kind of question is also there in H.C. Verma, and this is a much extended version of whatever we solved before. I had taken this solved example, right? This one, this particular example. This is very similar to that question. So let's see how do we solve this. Let's visualize it first. Alright. So the particle enters a sharply bounded region of magnetic field. So let's imagine this particular region of magnetic field. On this side there is magnetic field, on this side there is no magnetic field. So this is that region where your magnetic field exists, and that magnetic field is B. If you draw a perpendicular, let's say a perpendicular to this magnetic field, then it makes an angle theta to it. Then it makes an angle theta relative to the normal of the boundary line. Oh, now that theta can be of both the ways. So there could be two different answers actually for this particular question. So if it enters like this versus if it enters like this, because both of them can have the same angle. So let's just take one of the cases and then you will understand how to do the other case also. It's very similar. Okay. So let's say we take this particular charge particle to enter like this, making some angle theta over here. Now the moment this charge particle enters, it will experience a force V cross B and it will go in a circular path. So it will probably go like this maybe, and it will come out here, and then exactly it will come out with the same speed, same angle also. So if you draw a perpendicular here, you will notice that this particular angle will still be theta only. This particular speed will still be V. So it does stay inside this magnetic field for a short duration. This is one possibility. The second possibility would have been, imagine instead of this, instead of it entering this way, imagine I showed, see here I showed it from the lower side. Now what if it entered from the upper side like this, So in that case, okay, 1 second guys, let me show it here only because I will not have space then. If it entered from this side, then it will again make a circle, but it will stay for a longer duration before finally coming out, and it will come out again like this. So it will stay for a longer time as compared to this time. This will be complementary arcs, you can say. If this is one arc, if you try to fit it, it will exactly fit here. That's what it will look like. Is that clear, guys? All right. So now, thank you so much, Ravi. Means a lot, man. Means a lot. I'm so glad you are here, and continue watching all the classes because it's all for you. Now, to find the time spent, here is what I do. If I'm able to figure out somehow what is the angle subtended by the arc, that's enough for me. Because 360 degrees takes time period of t, 180 degrees will take half the time, 90 degrees will take 1/4 of the time, theta will proportionately take that much time in that particular arc. So the whole problem now is about finding that angle which is subtended. So if I draw the radius like this, I just need to figure out how much is basically this angle. It might not be theta by the way. How do I find that angle? Guys, think about it. Okay. If you are not able to visualize how to find that angle, again drop a perpendicular here. Now see, if this is theta, this is 90 minus theta, this is again theta. If this is theta, obviously because it's an isosceles triangle, this will be also theta. Anyways, if this is theta, this will be 90 minus theta, this will be theta. In this isosceles triangle, this is that arc which is there, this is the center which we are seeing, this is that radius, isn't that right? This is that angle which I wanted. Can you guess how much this angle will be? Because the sum of the angles will be 180 degrees. So it will be nothing but pi minus 2 theta. Pi minus 2 theta. And I am already seeing pi minus 2 theta at many places. Is that right? Okay. If it was this kind of scenario, then believe me, this whole angle which was subtended, yep, can you guess what it would be? Exactly complementary of that. Yeah, so it will be exactly complementary of that. So yeah, you will have to find it exactly the same way, drop a perpendicular and you will get it. Okay, so try it out. That is your homework, but this problem I will do it for you. Now once I know this, that is more than enough for me to solve the question. For a revolution that is 2 pi radian, the time taken is t. So therefore, for an arc which has 2 pi minus theta, how much is the time? That is the question. How much time does it spend? So that time by unitary method will be t divided by 2 pi multiplied by 2 pi minus theta. So therefore, our time period was, remember, 2 pi m divided by qb. This again divided by 2 pi, and this was 2 pi minus theta. So 2 pi cancels. So it will be m divided by qb into 2 pi minus theta. M divided by 2 pi, qb into 2 pi minus theta. If you want, you can, here 2m is there. No, this is not going to be working out. This 2m, 2 pi, no. I think this options are for the other scenario where, you know, it is entering from here and spending more time. But otherwise, you know, this particular solution is correct. This options will not work for this scenario, right? So maybe if you take the other scenario, then these options will work out. One of these options will work out. Most likely it will come out to be option A or something, or B or something. Okay, so that is how you need to solve the question. Did you understand this? How to solve this particular question? Very interesting. You have to figure out what is that arc subtending at the center. Once you get that, your job is done. Because this was theta, this was you know, other angle, and you just figured it out over here. Great. I'm just thinking, did we? Yeah, perfect. This was 90 minus theta, yep, perfect, nothing wrong. Awesome. Now let's take another scenario. See, we started our discussions with different angles and different scenarios. First, it was at rest, no change. It moves with uniform speed if it was parallel or anti-parallel. Then the next scenario was the field was perpendicular to the velocity, it goes in uniform circular motion. Now the last scenario over here, is when the velocity is not perpendicular to the magnetic field. So imagine a scenario. Where my velocity is making some angle with the magnetic field, with my magnetic field. So here is what I will do. I'll break that velocity into two segments. One velocity will be parallel to the magnetic field. I know that parallel velocity will never be affected by it, no force. And the other component perpendicular, and I know perpendicular component will experience some kind of force. Perfect. So let me break it into two segments. One is that perpendicular component, other is that parallel component. That's all. One is that perpendicular component, other is that parallel component. So let me redraw this entire scenario. Magnetic field is like this, as before. This is your V parallel, this is your V perpendicular. V parallel will be obviously V cos theta, V perpendicular will obviously be V sine theta. Okay. Now, think what will happen to V parallel. V parallel, nothing will happen. It will stay the same. This will not experience force. So, there will be no force on the parallel component of it. So, it will continue its journey as it is. So, it will just move uniformly. Move uniformly. There is no change. Move uniformly. There is no change in V parallel. So, this particular velocity will obviously be constant. You cannot change it only. Neither direction nor magnitude. But this one, I want you to visualize what will happen. For the sake of visualization, I'll just make you see this in 3 dimensions. Make you see this in 3 dimensions. Imagine this particular plane. Look at it sideways. Imagine this velocity here. Imagine this velocity here. And imagine this magnetic field coming out of the plane like this. Visualize, guys. Just visualize this magnetic field coming like that. V cross B will give me a force which is inside. That means that force will be in that particular plane. That force will be in that plane which I am making you visualize in 3 dimensions. The magnetic field is coming out of the plane. Velocity and the force are within that plane. So, this is a transverse field. Transverse field, we know what happens. It will do a uniform circular motion. So, that's why this particular particle is just going to go in a circular path, something like this. It will go in a circular path, something like this, guys. See if you are able to visualize in that particular plane, like this. So, the motion of that charged particle due to the perpendicular component will be like this, and this motion will be uniform circular motion. Are you able to visualize? So, this charged particle is going to go like this. Imagine a plane like this. In that plane, it is going in a uniform circular motion due to the perpendicular component. So, that time taken to complete that uniform circular motion is still the same irrespective of the velocity. It is 2 pi m by charge into velocity, charge into field. The radius though will be mass into perpendicular velocity divided by charge into the field. But this V is V perpendicular. That's it. That is the major difference. Which radius am I talking about? Over here. This radius. This particular circle will have some radius, right? So, that is the radius that I am talking about. Everybody is able to visualize these concepts. So, the perpendicular component is performing uniform circular motion of radius m V perpendicular, where V perpendicular is V sine theta by QB. Time is still the same and the parallel component is anyways unaffected. Now, combine both these effects together because both are happening simultaneously. Right now, we visualized it separately. We thought this independent of the other. Now, you combine both these effects. Combine both these effects together and think what might happen. Combine both these effects and think what might happen. You add both of them. Combine. Recombine. Here we had split. Now again combine. It is doing circular motion in this plane and at the same time it is going forward. It feels like it is tracing the path of a coil of a spring. You have seen a spring. The spring is like this. It is circle drawn in different planes. You are shifting that plane. So that plane is moving with a speed v cos theta, and on that plane you are drawing those circles. Are you able to visualize it? Just think about it like this. So this was that plane. You are drawing that circle, but that plane keeps on shifting. So you are drawing that circle, but that plane keeps on shifting. So if you look at it from this side where the plane C is in the front, you will always see circular motion, but the circle is going away from you or coming towards you. That's the only difference. But that plane is shifting at a constant speed of v cos theta. Oh, perfect. So how will that motion look like, sir? Make me visualize. The answer is, it will look something like this. This motion is the coil-like motion. This is called as a helix. The motion is called helical. Okay, that's the adjective form. That is the noun form. Helix is the name of the path. But when you are describing the motion, so that will become an adjective form. So that will be called helical motion. So helix or helical, which is like the shape of the coil of a spring. So I can say this is the shape of a coil of a spring. Coil of a spring shape. That is what it looks like. This particular line which goes within that helix, that will be the axis of the helix. There will be radius of the helix, and there will be also pitch of the helix. Pitch means after one coil or one turn or one revolution, how much has the plane shifted by? That is called as the pitch of the helix. That is called as the pitch of the helix. So let's define what is the pitch. So if you take a helix, and this is the helix, and it will keep on continuing its journey, guys. This is your helical motion. This is your helical motion. So you can see after one revolution, it has moved by some distance. This is called as the pitch. So pitch is basically the shift after one revolution. After one revolution. In order to calculate the pitch, it's very simple. You just have to find how much will this plane shift by in one time period. We know the speed of the plane is v cos theta, and in one revolution, meaning this time. So hence, I will just say it will be nothing but the speed in that parallel direction, multiplied by the time of revolution. So speed in the parallel direction is v cos theta multiplied by the time of revolution, which is t, which means it will be v cos theta multiplied by 2 pi m divided by qb. That is what that pitch will be. Similarly, we can also talk about what is the radius of the helix. That radius of the helix is same as the radius of the circular motion. So the radius of the helix, radius of that helical motion or helix will be nothing but the radius of that uniform circular motion, which is mass into v perpendicular by qb, but v perpendicular is v sine theta divided by qb. So it is this formula. Okay, the radius is still the same. It's just that the circle is moving ahead. So the radius of that helix is the same radius which you get in the uniform circular motion. So if you visualize it in 3D, it looks something like this. The charged particle is going like this, round and round and round, and it keeps going ahead. This helix has got distorted at the end. So let me remove that, or else you'll get confused. That's it. Okay, so it will keep going like this. So after one revolution, this gap which you see is basically that pitch. Exactly one revolution, what is that gap? So that is called as the pitch. Radius of the helix is this one. Okay, radius of the helix is basically this thing. Radius of that circular motion. Cool? Everyone? Understood? Pakka? Clear? Visualized? Amazing. Amazing. Vemonaya, this is an English channel, man. Akash, this is an English channel, man. Hi yourself, Ritu. Welcome. Rahat, what to say, man, because I have such amazing students. No, that is the reason. For you guys only, Shreyas Sir is like this. Or else I would be Buddha only. Full Buddha. I have to stay with young people, no? So that's why. Okay. Let's solve some questions coming up on your screen. And this is one of the questions. Let's see. A charged particle of mass m and q is projected in a field with a speed so much I cap, so much j cap. The pitch of the helical path is given by, interesting question, they have not given the total velocity but components have been given, and magnetic field is in I cap direction. Okay, let's visualize it one by one. So magnetic field is here. So this is B I cap. The velocity has I cap also and j cap also. Okay, so the I cap component is like this, the j cap component is like this. Okay, so I cap component is V1 I cap, j cap component is V2 j cap. Net velocity will be obviously like this, but I'm not interested in the net velocity. I'm more interested in the components because that's what is going to matter. So now you can perfectly think that this particular expression is actually V perpendicular. This particular expression is in the parallel direction. So this is V parallel. So this is V perpendicular. This is V parallel. Okay. So this was V perpendicular. This is V parallel. So if I am interested in finding out what is it, the pitch of the helix. The pitch of the helix is whatever is the V parallel velocity into the time period. V parallel is nothing but V1. Time period is 2 pi m divided by charge into B. So 2 pi m V1 into QB. So that is option A, my dear. That is absolutely right. What will V2 be used for? That will be used in case you want to find the radius. Radius will be m V2 divided by QB. That's a different story, but we were asked pitch, so parallel component will be used. For radius, perpendicular component will be used. So both kind of questions can come. Clear? Fine? Fair enough? Awesome. Now, let us see what will happen. Let us see what will happen if both electric field and magnetic field are there. If both electric and magnetic field act on a charge, then here are the things. First of all, if this charge is moving with some velocity, let us say the electric field is in this direction. Now, no matter what that velocity direction is, doesn't matter. What matters to me is what is the direction of the electric field. Exactly in the same direction, you will get the electric force. So the force due to electricity, is exactly in the same direction of the electric field, and the magnitude will be charged into the electric field. But for that charged particle, when you consider the magnetic field's effect, so let's say for example now the magnetic field, let's say the magnetic field is in some other direction like this, which we have been drawing before, then you will take V cross B, and V cross B might be somewhere like this, I don't know, maybe here, and this will be the force due to the magnetic field. So this force due to magnetic field we all know is nothing but Q into V cross producted with the magnetic field. It's in some weird direction, right? It is in some weird direction which is we saw is perpendicular to both. So when both of them are there, then the net force which it will experience, is whatever force electric field will give plus whatever force magnetic field will give, So if you take the vector sum of both of them, so on the same charge moving with the same field, same speed, sorry, both the forces will come. Electric force will also come. Magnetic force will also come. The vector sum of both of them, wherever it is, I don't know, just taking randomly here. So the vector sum, whatever it is, this is the net force acting on it, and this net force will be then, because Q will be there, Q will be there, V is there, cross product is there, plus is there over here, plus is there over here, and then you have the field over here, and here you have the magnetic field over here. Charge can be taken common if you want, but this total expression, my dear, this is called as the Lorentz force. Yeah, Lorentz force, that was the name of the title of our lecture. This expression is called as the expression for Lorentz force. So Lorentz force is basically when both effects are considered. Maybe one of the fields might be 0. So that is called as your Lorentz force. Lorentz force. The force due to electric and magnetic fields on a moving charge particle. Simple. It's just the vector addition of both of them. Yeah. Clear? Pakka? Done? Dusted? Now let's take a special case of it, because the forces can be in any weird direction. So many possibilities are there. So you cannot keep on studying every possibility. So it depends from case to case basis. Sometimes electric field, magnetic field might be perpendicular, parallel, anything. So one such crucial case is this one, where the magnetic field, electric field and the velocity, all of them are perpendicular to each other. Such a scenario is called as a crossed field. What is it called? Crossed field. Where you will notice the velocity is perpendicular to electric field, velocity is also perpendicular to magnetic field, and even electric field is perpendicular to magnetic field. All of them are basically mutually perpendicular. Such a scenario is called as a crossed field. Now, why is that scenario important? You will understand later. But first, let's see what is going to happen because of this. Observe, magnetic field is inside the plane. Electric field is like this, vertical. The motion of the charged particles is horizontal. Let's see what are the effects. Because of electric field acting down, because of the electric field which is acting down on that charged particle, no matter how it is going, the force will also be in the same direction. The force will also be in the same direction. So force due to electric field will be downwards. Magnitude wise, it will be nothing but charge multiplied by the electric field. If you just consider the magnetic field is inside the plane of the board. Alright, so magnetic field is inside the plane of the board. The charged particle is moving like this. The charged particle is moving like this. So the force acting on it, V cross B, will come out to be upwards. It will come out to be upwards, and the magnetic force will be QVB. Will be QVB. Now there is a tug of war between these two forces, if you notice. Electric force is down, magnetic force is up. So there is a tug of war. Are you able to visualize this? See, this charged particle, Pavam fellow, this charged particle is trying to move like this. There is a tug of war between the magnetic and electric force. Magnetic force is pulling it up, electric force is pulling it down. So one of them will dominate over the other, and there will be a net force either upwards or downwards, or maybe they might just cancel, maybe. So if the electric force is more, the net force will be up, and that's when you will see the charged particle will deflect like this, when electric force dominates. If magnetic force is more than the electric force, net force will be downwards, and then the charged particle will deflect downwards like this. But just in the case where they balance. Basically, the electric force balances each other. In such a scenario, what happens is electric force is Q into E, magnetic force is Q into V into B, Q cancels, E will be equal to V by B, meaning electric field is V times magnetic field, or V is electric field by magnetic field. By chance the speed is the ratio of electric and magnetic fields, then the net force is 0. It will neither go up nor go down, it will go in a straight line. So meaning the velocity is uniform. It is just going to go in a straight line without any deflection. There is no deflection at all. There is no deflection at all. Crazy, right? Now this formula is very important because many times you will just get a direct question. What should be the field so that this particle moving at some 200 meters per second should not deflect? You will know magnetic field, you know the speed, you will find electric field. Or you will know electric and magnetic field, at what speed should you throw so that it does not deflect. Immediately take the ratio, you will get the answer. E by B is that speed at which a charged particle in a crossed field only will be undeflected. Now you will be like, sir, what is the use of it? What will I get by not deflecting it? What am I achieving in life? Like by rotating the charged particle, we got a cyclotron. What are we achieving with this? Okay. All right. Yes, it is PWJ English, man. Yeah. Thank you, Chaitra. Yeah, very good. We need more people like you. Hi, no one more. Welcome. Hi, Om Prasad. Good evening. Hi, PVR King. Good evening. What is the use of this? Just imagine I have a bunch of charged particles coming from some gun, electron gun, proton gun, whatever you call it. And I want only those particles with a particular speed. It's like saying I have a class full of students. I want exactly those students who have got 90 percentile. Even 1 percentile more or less I don't want. Then I will use this formula. You tell me what speed you want, bro. Oh, you want 100 meters per second. Huh? Okay. Magnetic field, how much you are giving me? Okay, this much. Okay. Electric field, do one thing. Put this much so that the ratio will become 100 or whatever, 200. When you adjust that field, exactly those particles with that speed will go straight. All other particles will go up or down. So what you do is in front of this, you create a small hole. Rest of it is blocked. Only those particles will go out of that hole. So you are selecting the velocity which passes straight. So this is called as a velocity selector. What is this called? This is called as a velocity selector. All other velocities are eliminated. Like in Squid Games, elimination happens. So you are eliminating these particles which are not the chosen ones. So these are the chosen ones who can pass through that hole. Understood, guys? Isn't it an amazing concept? Of course, Aritra Ghosh, definitely, man. You can. And that's the whole point of these lectures. Doesn't matter whether you are 9th or dropper. It is for everyone because I am teaching for proper JEE level content from basics to your JEE. Everything, all concepts, all formulas, everything which is there for JEE Mains plus advanced is being taught here. You don't have to watch anything else if you want understanding, problem solvings and application. More problem solvings are going to come in the due course. But yes, these are proper classes to make you understand the entire lesson altogether. That's what you need. You have time also. Okay. This is called as a velocity selector. Let's see if we can solve this question on velocity selector. Oh, this is not a question on velocity selector. My bad. Let me just make a problem on velocity selector. A charge of 1 microcoulomb is is accelerated to a speed, actually let's put -1 microcoulomb is accelerated to a speed of 500 meters per second. If it passes through a crossed field, find B undeflected, find magnetic field, given the electric field is generated by two plates at 200 volts potential difference separated by 1 centimeter. That's the question. Okay, very interesting question. Let's see if we can figure this out. A charged particle is accelerated by some speed and it reaches a speed of 500. Now you want to maintain that speed. You don't want it to be deflected. So you have applied magnetic and electric fields. You have to find the magnetic field. Electric field is not given directly. It is given indirectly. How? The electric field is generated by two plates which are maintained at 200 volts difference by 1 centimeter difference. Okay. So the logic for this problem, visualize it. The charged particle will go like this. Okay, what is the charge? It is -1 microcoulomb. What is the speed? It is 500 meters per second. That is not going to change. It is going to be constant. Magnetic field, I do not know. We have to figure that bit out. But that is the whole point of this question. Magnetic field is unknown. But electric field, we know it indirectly. How, guys? Think. How do I know electric field? See, it is mentioned that there are two plates which are generating that electric field. If you remember, electric field was potential gradient. If you remember this, electric field was negative of potential gradient. Here we are talking about the magnitude of the electric field. So we are not putting the minus sign. So electric field is how much voltage difference is there upon the distance that you are traveling. So that magnitude of that electric field is that voltage that you are giving between the two plates upon that distance. So it will be nothing but 200 and 1 centimeter means 10 to the power -2 meters. This will be meters, this will be in volts. So that will make it 2 into 10 to the power 4 volt per meter. That is the magnitude of the electric field. Got it? Once we get that, easily we can figure out what is the magnetic field, because V will be equal to E divided by B. Therefore, B will be equal to E divided by V. V comes down, B goes up. Electric field is 2 into 10 to the power 4. So 2 into 10 to the power 4. Whole thing divided by speed 500. So just put 500. 2 zeros will vanish. So it will become 2 by 5 and 10 to the power 2, which is 2, 1 0 1 0 and divided by 5, which will make it 40 Teslas. That's huge, but whatever it is, we have to put it. So 40 Tesla is the answer. So sometimes, they can add one step, because just giving you V and B, finding E will be very simple. So they just add 1 or 2 steps to just make it look like a JEE problem. Otherwise, these are very laddu questions. So E is dV by dr. That is the concept we have used. Another good question. A uniform electric field and a magnetic field both are existing. Electric field is in J cap magnetic field is also in J cap. So this is not a question of crossed field. A particle is thrown with a speed of I cap. Oh my god, it's perpendicular to both now. The y coordinate of the particle when it completes its full revolution in the xz plane. So 100% this is a either good JEE mains question or a normal JEE advanced question. Alright, so let's have a look at it. First, electric field is in J cap, magnetic field is in y axis also. Motion is in x direction initially at least. So the motion of the particle initially at least I can say it is V naught I cap initially. Okay. Magnetic field, man, and electric field both are in this direction. Magnetic field as well as the electric field both are in this direction. So electric field is E naught J cap and magnetic field is B naught J cap. Oh, what will happen? I think let's consider one by one, only then it makes sense. Otherwise, if you try to think together, right, it will become very confusing. So let's just for now focus on magnetic field, then we'll focus on electric field, and then we'll combine both these effects. If I ignore the electric field for now, then magnetic field and velocity are perpendicular. Oh, this is a transverse case scenario. So V cross B will be force. So force will be directed this way towards me. So the magnetic force will be like this towards me. So it will do a circular motion in this plane, perpendicular to the plane of the board. So visualize this, something like that. Your magnetic field is like this, magnetic force will be like this. So it will perform a uniform circular motion in this plane. Are you able to visualize this now? In this plane it will V cross B. Oh, sorry guys, not that plane. My bad. I drew a wrong plane. Velocity is like this, so it will be horizontal plane. My bad. Let me redraw it again. So sorry. Yeah, visualize this plane. The magnetic field is out of the plane. The velocity is like this. The force is like this. So the direction of the motion will be in this plane, circular motion like this. See if you are able to visualize this now. Which plane will this be? Yeah, this will be obviously the z axis. This will be obviously the x axis. So this is xz plane. Are you able to think how it is? It is in the zx plane, and y axis is exactly perpendicular where the magnetic field is. So because of the magnetic field, it is performing uniform circular motion in the zx plane. Now think what will happen to that same charge? What will happen to that same charge because of the electric field alone? Because of electric field of E naught J cap alone. Well, this charge will just experience a force in this direction, will experience an electric force in this direction. So it will accelerate like this. So the motion of the charged particle, all right, will have a velocity in this direction. So it will start gaining, it will gain velocity in the y direction, will gain velocity in the y direction. So now think there is uniform circular motion happening in horizontal plane, and that horizontal plane is getting lifted up slowly because of this electric field. So if I had to draw, I would draw it like this. It's little crazy to draw, but I will make a sincere effort to draw it. Okay, just visualizing is very important. That's why I'm drawing it, nothing else. 1 second. Yo, what is this? 1 second, guys. It will take little time, but I feel it will give you a clear idea of what is exactly happening. This is one plane and this is another plane, and what will happen is this particular charged particle will start from this plane. Otherwise it would have completed a circular motion in this plane, but because of this electric field, that particle will get lifted and come to this plane. Visualize, it will not just come back to the same plane, it will go like this and come over here. Are you able to think about it? It will come here. See if you are able to visualize. This is how that motion will be. Kind of an helix, but not exactly a simple helix, because it is accelerated in this direction. It's like a pitch of the helix is increasing, because in the next revolution it will go even more. In the next revolution it will go even more, because it is being accelerated in this direction. So the planes will not be equally spaced. The pitch will not be equal. Visualize it that way. The pitch won't be equal. Yeah, everyone? Amazing, amazing. So the question is that what is the y coordinate? And my dear friends, this only is that y coordinate. Whatever is over here, right? This exactly is that y coordinate after when it completes its first full revolution. So this is one revolution. So one revolution will take exactly one time period. So now I know how much time it will take. Time is time period, which is 2 pi m divided by q into b. That's it. So that is the time. So if I want to find the y coordinate, y is the displacement, and displacement, my dear, is nothing but ut, initial velocity in the y direction, into time, plus half into acceleration in the y direction into t square. There is no initial velocity in the y direction, so this quantity is 0. Acceleration in the y direction is whatever force you get upon the mass into the time square. Now that particular force we already know, this electric force is nothing but the charge which is there. I think it is how much? Q, guys. Okay, it is nothing but Q multiplied by E naught. So the force which you will write, it will be nothing but Q multiplied by E naught. Q multiplied by E naught. M is there, and the time which is there, I'll just substitute it from here. So that time will be nothing but 2 pi m divided by Q b naught, but this whole thing square. So that is my y coordinate. Solution is barely 4 lines, but the thought process is very good. And that was what is the crux of that problem, and is going to take a lot of time to actually visualize and put it into those equations. So we initially ignored electric field, we saw magnetic field. It was just making the particle go round and round in xz plane. The electric field was pushing it up in the y direction. So if I combine this motion with this motion, I will think as if the uniform circular motion is being shifted in a different plane, in a parallel plane horizontally up. And when I shift it vertically up, keep in mind it is accelerated because the force is there. The force will cause an acceleration in the y direction. Acceleration is force by mass. Force is charge into the field. So I have substituted force as charge into the field. Time taken is 1 revolution's time, 2 pi m by qb. Solving this, you will get the answer as 2 pi square m E naught by q b naught square. Is that clear, guys? Everyone? Is it amazing? Thank you, Heggies. Man, demand is there from a very, very long time. I have an exam based on this tomorrow and I saw your lectures and still not able to solve questions from Lorentz Force. Can you tell from where to solve now? Which kind of exam is there, man? Is it coaching or boards? For boards, so you will just go for NCRT and all of that, NCRT exemplar. But for for coaching, if this particular topic is there, if your module is not good enough, then I would suggest use H.C. Verma, objective questions and short answer questions to build the base. Okay, just to build the base, and maybe a couple of questions from the start of the exercise, just to build the base, nothing else. Once you reach a decent level, then you can either go to Cengage or DC Pandey. Preference will be DC Pandey, Arihant books. Okay, so if you have those objective books for DC Pandey, use those books, solve that material. It's a good material. But if you already have Cengage, you can use Cengage, but Cengage I would not prefer. DC Pandey is better. Okay, and then you can go for PYQs. That is the right order of solving these problems. Okay, coaching exam means this only: H.C. Verma, DC Pandey, and then you go to PYQ books. PYQ books you can use Disha publications or Arihant publications, or if you are coaching model, whatever is that. So that is the right sequence. Amazing. So we done this also. Now that we understand a moving charge will experience a force called as the Lorentz force, we extend this idea to the current carrying wires. At the end of the day, a current carrying wire is nothing but a part which has charges in motion. So if a moving charge can experience force, why can't a current carrying wire experience force? Because a current carrying wire anyways has moving charges. So hence we come to that conclusion that if a moving charge in magnetic field can experience force, therefore I say a current carrying conductor has moving charges. So since a current carrying wire has moving charges, therefore, or it is implied that a current carrying conductor experiences force in magnetic field. So how much is this force? Let's write it down first. Now the wire can be a long wire also. So what we do is we generally take a small part of that wire, and let's say that small part of that wire is this one, which has some current I, and the length of that wire is dl vector. So dl is basically the element of that wire, and the direction is same as that of the current. This is the element of the wire which is carrying that current. The direction is same as that of that current. And let's say there is a magnetic field in this particular region. Let's say that magnetic field is B. So if you want to find that force, all you need to do is take dl, cross product it with B, magnetic field. dl cross B will give you the force, and the magnitude I'll just show you. So first the direction, the force will be dl cross B. dl is here, B is here. So the force will be like this. But since it's a small conductor, the force will also be small only, no? So the force will also be very, very small. So that force on that element, the force on that element dF bar is given by ideal bar, and then you do cross product with your magnetic field. That is the answer. Very similar to QV cross B. Instead of charge there is current, instead of velocity there is length. Rest of the things are same. So it's a cross product between length and the magnetic field. It is a cross product between the length and the magnetic field. So this force, please keep in mind, it is perpendicular to the length also, and it is also perpendicular to the magnetic field, both. So if there is a angle over here, then it will be nothing but I dl sine theta will be there, multiplied by the magnetic field. That's it. Now if that wire is long, imagine that wire is a long wire, long curved wire, whatever it is, then every part will experience different forces. Every part will have different lengths and directions. So you will have to find the force at every single place. Here the force is like this, here it is like this, here it is like this, I don't know, and this is placed in some whatever magnetic field like that. So you will have to find forces at every single place and add it up to find the net force. So on a long wire, I will say, on a long wire, the net force F will obviously be integration of all the small forces. So when I do integration, it means it will be integration of I dl cross product with the magnetic field. So the integration or the summation, vector sum of all of that. So that will be for a long wire. Okay. So if you take a long wire, this is different from an element. This was just an element, this was a long wire. You will have to integrate the force throughout that length. If it is a straight wire, things are very simple, guys. If it is a straight wire, then things are very simple. Imagine it is like this. This is the length. It is carrying just current I, and let's say the magnetic field is like this. Magnetic field is like this, making some angle theta. The force acting on it, simply will be I know it will be I will be there, L will be there, cross product with B. But if you try to find the magnitude, it is even more simple. The magnitude of this force will be simply I L sine theta multiplied by B. ILB basically sine theta. So for a straight wire, it is just ILB sine theta. Current into length into B into sine of the angle between length and the magnetic field. Simple. For a straight wire. This was a straight wire. Now I know you are not so happy about this curved wire because you will have to integrate it. But I'll tell you something. Most of the times you will not have to integrate it. Okay? Most of the times you will not have to integrate it, and that's the best part. So if by chance you have a curved wire also, okay, let's say you have some curved wire which is carrying some current. Let's say it is placed in a uniform magnetic field. Let's say it is placed in a uniform magnetic field. Then to find that force, all you need to do is just join the start of the wire to the end of the wire. Just join the start of the wire to the end of the wire. This becomes the effective length of that curved wire. So whatever force acts on the straight wire joining the ends with the same direction and the same current is the force on that curved wire. So that is the most amazing thing on this. So whatever net force will come, on the curved wire will be exactly the force on that effective straight length, and when I say effective straight length, that means I will take L effective, take L effective, current is still the same, whatever that same current is there, multiplied by the magnetic field. So instead of taking multiple integrations and all of that, just ignore all of it, just draw a straight line. Whatever force will be there on that straight line, which is a simple formula, will be the answer. That's all. So this helps us solve the questions very easily without using integration. So very, very important. Force on a curved wire is the force on the effective length between those two endpoints of that curved wire. And for a straight wire, it is a very simple task. Got it? Everyone? Yeah? Hi Richard, welcome man. Yep. Awesome. Guys, don't do this. Test is tomorrow and you watch my lecture today. I know I can't help it, nor you can help it, nor can the school help it, because I am planning my lectures at own space. Coaching will plan at its own pace. But I am trying to cover up as much as possible, you know, in the time that we have. Okay, so the next chapter maybe we will do is Biot-Savart's law and Ampere's law chapter next Friday. Then we'll go on to EMI, then we'll go to AC. We'll try to do all the major chunks as soon as possible so that you do not face any difficulty. Then we'll go to ray optics, wave optics, modern physics. That will complete your 12th. It's barely another 6-7 classes or 8 classes, hopefully. Okay, done, understood? Shall we go ahead? Okay. Now imagine a special scenario. Imagine a special scenario where your wire starts and ends at the same point. Crazy, right? Such a thing is called as a current loop. Such a thing is called as a current loop. Now that current loop is placed in some uniform magnetic field. That current is placed in some uniform magnetic field. This is uniform magnetic field. For such a scenario, if I want to find the force, what will I do? The start and the end is the same. So what will be the effective length? Obviously, it will be 0. Basically, it will be null vector. So if such a thing is a null vector, that means the force on a closed loop carrying current will always be 0. So very, very important statement, guys. So the magnetic force, I can say, the magnetic force on any current loop in an uniform field, uniform magnetic field, is 0. Very important statement. Remember this line. This will be useful for again many problems. You have any magnetic field, okay? So uniform field, the net force will always be 0. Clear? Done? Understood? Pakka? Very good. So the conclusion is the magnetic force is IL cross B, and that is the most commonly used formula. Even if it is a curved wire, still we can break it down into effective length. But if it is a closed loop, then the effective length is 0. So the force will come out to be a perfect 0. Okay, amazing. So let's start with some questions, guys, before going ahead. Yeah. Let's take this question first. Let's take this question. A wire is bent into the shape of a semicircle. The radius r lies in the xy plane with its endpoints fixed at this. A uniform field exists in that space. A current is flowing from minus r to plus r in that arc. Find the force vector acting on that arc. Okay, so that arc is there in the xy plane. So let's say this is the y-axis, this is your x-axis, this is your origin. The wire is bent in the shape of a semicircle in xy plane with two endpoints fixed at minus r and plus r Okay, minus R and plus R. So minus R and plus R means it will be like this. So if this is minus R, comma 0, and this will be plus R, comma 0. Y coordinate is 0. This is minus R, comma 0. This will be plus R, comma 0. The current is going from minus R to plus R. That means the current is going like this. Magnetic field is B naught K cap. It is coming towards you. The magnetic field is coming towards you, B naught K cap. Okay. Question is find the force acting on it. Guys, what do we do? The moment you have any curved wire, what will we do? The force acting on that curved wire is the force acting on the effective straight wire. What is that effective straight wire? Take the endpoints. This is one endpoint, this is another endpoint, join them. That's it. This is going to be the effective length. Can you guess what that effective length will be? From here to here, the distance is 2R. R plus R is 2R. So it will become 2R, but it will be I cap. That's all. So that's it. It will be nothing but current into effective length multiplied by magnetic field. So current is I only, effective length is 2R I cap, magnetic field is B naught K cap. So it will become 2IRB multiplied by I cross K. What is I cross K? IJK. I cross K will be negative J. Is that right? So hence this particular answer will be, because this will be I cap cross K cap. So this will become negative 2IRB J cap. That is the answer for that curved wire. Check this out, which is option A. Minus 2IRB J cap. Clear? So force on a curved wire is the force on the straight wire. Very simple. Another interesting question is over here. Look at it. A wire loop is there and it is placed in a magnetic field which is normally pointed in that plane. What is the tension developed in that loop due to the force? Crazy. Okay, crazy. Let's try to solve this. There is this loop. The magnetic field is perpendicular to that loop plane. The magnetic field is perpendicular to that loop plane. That means it is something like this. This is what the magnetic field looks like. The current is like this. Current is like this. Okay. Now, apparently it so happens that the tension is created inside that loop because of this scenario. Question is, how much is the tension? First, we need to understand why on earth will tension come. What is that cause? Because I am not able to see it very clearly right now at least. So first let's analyze that. Then maybe it makes sense how to calculate it. Okay. Now if I take any part of that wire, let's say I consider this particular part of that wire. It has a length L like this. Magnetic field is vertically up at that scenario, at that place. If I do L cross B, well, guess what? The force comes out like this, out of the plane of the board. So that force dF will come this way, out of the plane, out of the plane of the board. So in this region, the force will be like this. If I do the same thing here, it will be like this. Here 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 it will be like this. Now suddenly it makes all sense. I am pulling the loop, that wire, from all sides. So the loop is pulled and stretched outward, because of which there is mechanical tension. That is the reason for it. So now it makes sense. It's like, you know, you're pulling that loop from all the sides, so it's trying to expand. So when it tries, anything tries to expand, it will have tension within it. Okay, great. Now, how do I find out the tension? Many people do it by difference, meaning derivatives or differential calculus, by taking a small element and drawing all the free body diagram for those elements. I will not do all that. It will be very lengthy. Instead, what I will do, I will consider exactly half of the loop. Exactly consider half of the loop. Okay, don't even worry about the other half. All right, this is exactly a semicircle. Now, for that semicircle, with that magnetic field, there will be some net force acting on that semicircle. That net force can be found out easily if you consider the effective length to be like this. This is your effective length, and effective length will be basically 2r, and that effective length will be in this direction. Considering the current is going from here to here, same direction has to be taken. So if length is here, magnetic field is on the top, length cross field will come out to be like this. Check this out. Length cross field will make that force come this way. Is that making sense? So that force due to magnetic field will be I L effective into B, L effective being 2r, because that is the diameter's length. Why did I do it? See, this force which is there due to magnetic field should be compensated, balanced by somebody, and that is coming from these endpoints. Because I considered semicircle is just a part of that circle. So the other half will be pulling it, and that will be the tension. So the tension will come like this as well as like this, T over here and T over here. So now we can see Fm is 2 times of T. Basically, it is being balanced. So 2IRB is 2 times of tension, 2 cancels. So therefore, tension is IRB. IRB is option A. That's it, done. So without calculus, without derivatives, without elements, we were able to solve it. How? Because I used the trick of effective length. So I took the effective length to be 2r. So the force will be like this. That force will be balanced by tensions on both the ends of that wire. Just like you used to solve Newton's laws, a string is there. Ends of the strings are under tension when being pulled. So these two ends are being pulled from this side, is being balanced by magnetic force on this side. So solving it, I get IRB. Isn't it easy, guys? Yeah? Sir, my hard work is not equal to anything. Kanish, don't say that. What do you mean by not equal to anything? Meaning, is it equal to something? Or is it equal to everything? Is this chapter 3? Yeah, you can call it chapter 3, chapter 4, chapter 5, whatever you want. Okay. Now, there are these two interesting questions which I want to discuss at the same time. See, if I take a circle, and if I pass a current like this, and let's say there is some magnetic field, doesn't matter how, let's say in this case it is, I don't know, maybe towards you or away from you, anywhere. In this scenario, because it is a closed loop, the force acting on that loop will 100% be 0, for sure. But sometimes what they do, they will give something like this. Current is coming in and it is going out like this. And let's say the magnetic field again is, let's say, towards you. What will be the force on this loop? Now, believe me, the answer most likely will not be 0. Yes, this answer is 0, but this answer is not 0. Why? You should understand. See, a loop means the current should come back to the same point after rotating once, right? This, my dear friend, is not a loop. Yes, it looks like a loop, but it is not a current loop. Why? Because the current over here doesn't even go around like this, rather it gets distributed. Here it is I by 2, half, and here I by 2, current, electricity chapter, current, Kirchhoff's current law. Oh, it is getting distributed, crazy. Now it makes all sense. So, what will happen? This semicircle, the upper semicircle will have an effective length, L effective of 2r, and the lower semicircle will again have an effective length of 2r. So each of those semicircles will have their own effective lengths 2r, and each of them will experience force. So magnetic field is towards you, right? So length is there, field is here, length cross B will go down. So the force will be there 2 times. That's the main catch. Even this will experience force, even this will experience force. And each of these forces will be I, L effective into B, but I will be also I by 2. Keep that in mind. So I by 2, length effective is 2R into B. So it will become IRB, but that is the force on any one part. So the net force will be 2 times of IRB. So it will become 2IRB. That is your net force. Okay. So the net force on this thing is 2IRB. I by 2, current here, length is 2R. So I by 2, 2RB, which makes it IRB. That is for a semicircle, another semicircle also IRB, so 2IRB. This scenario is way different from this scenario. So you will see a couple of questions like this, where they will give you a square loop. What is the force on it? It will be 0. But if the current enters and exits like this, then you have to choose the effective length. So be careful. It might look like a loop, but it might not be a current loop. That is the catch. Got it? Yeah. Very good. Great. So, yep. So we have done a big deal. I think we can now take a small break before moving on to magnetic moments. So we'll take a small break, guys, and then we'll return. Okay? We'll take a small break. Welcome back, welcome back, welcome back. I hope I'm audible and visible to all of you. Yep, let me know quickly, guys, in the chat box. Yep, I hope you guys had your dinner and yummy dinner. Let me know quickly what and all you had in the chat box. Or were you just practicing questions or reading something? I just hope you guys take care of your health too, because it's not just about eating but also exercising or keeping your mind active apart from studies. So what happens is, you know, with JEE kids, most of the times they get so involved into studies, which is a very good thing, but also forget to take some breaks, take care of your health mentally and physically. So don't ignore that. It's not just preparing yourself for the exam day and staying fit for the exam day, but in general for your future also, it's good. So please don't sideline your mental and your physical health, right? Okay. So let's begin with the next concept. Before the break, we had spoken about how a current carrying loop or a wire experiences a magnetic force given by ILB. And we extended this concept to a current loop, saying that if it is placed in a uniform field, then the force acting on it is zero. But imagine if I ask you, will the torque acting on it be zero? Interesting. This is not experiencing net force, but is the torque going to be zero? I don't think so. The torque usually is there. And that's what I'm interested in, and that's what we will figure it out. So let's just take a random current loop and try to figure out what is the net torque acting on it. So let's do one thing. Imagine this is a current carrying loop. The current is going like this, like this, like this, and like this. The magnetic field is in this direction. Uniform field is there in this direction. Okay. Let's say the width of the loop is W and the length of that side is L. And it is making some kind of an angle, you know, with that magnetic field. It is placed at some angle. Now, if I see it from the side view, then probably drawing the forces and predicting the directions might become little bit easier. Say for example, if I concentrate on this element which is carrying the current in this direction, if I look at it from the side view, okay, the magnetic field on it is like this. The magnetic field on it is like this. So if I ask how much force is there, you will do L cross B. L is here, B is there. So the force on it will be inwards. Check it out. The force on it will be inwards. Similarly, if I ask you, consider this element where the current is going down, magnetic field is still like this. L cross B will be towards you, so the force will be directed out of the plane, like that. Similarly, if you consider this element, it will appear to go inside the plane of the board. This element will appear to come towards you. The magnetic field obviously still like this, no doubt. The force in each case, observe, L is inside, field is that way. L cross B will be downwards, so it will be like this. Here, magnetic field is that way, current is coming this way, so L cross B will be upwards. So these are the forces acting on the four sides of that rectangular loop. Out of that, this side and this side, meaning this one and this one, these forces are equal and also opposite. So if you notice, it is one is going inside, one is going outside, meaning one will be like this, the other will be like this. So these forces, if I call this F1 and F1, these forces F1 and F1, they will end up cancelling out each other without even creating any torque. They are collinear. They are cancelling and they are collinear forces. So they cannot create any torque. Remember, for creating torque, the force has to act along different lines. If I take this pen and if I pull it from the top and pull it from bottom at two different locations, collinear is not there, they are non-collinear. So that will rotate. But if I take this pen and pull it from both sides like this, then it is if I pull it like this from both sides, it is collinear and then it will not rotate. It will just stay there as it is without any torque. Like this it rotates because one force is here, other force is here. Those two forces are non-collinear in nature. So non-collinear will create torque, collinear will just cancel and it will not create torque. So now if you look at these two forces, that I think will create torque, because this one was for the top wire, it was going inside. So the force was acting down like this. This force is going to act like this upwards. If I call this F, this is also F. These are those two forces. They are cancelling each other force wise, but they are non-collinear. And because of this non-collinearity, torque is being created. This collinearity will not create torque, so no torque because of this. Is this understood, my dear warriors? Who is participating in the torque and who is not participating in the torque? This F and this F are in two different places, two different lines. This line is different from this line, creating a torque, whereas these two are along the same line, so no torque at all. So how much is that torque being created? So to visualize that, here is what I will do. Here is what I will do. Well, look at it from the side angle. Look at it from the side angle. Just look at it from the side angle. Nothing else. This is your magnetic field as it is still. One of the force is here like that, and another force is down like this. Another force is down like this. This is on the top. This is below. This is F. This is F. As you can see, this force is acting along this line. This force is acting along this line. There is some separation between them. That separation is of importance to me because that separation is the distance between these two forces, which will help me find the torque. Let's say I call that separation as D. Now these two forces act like a couple force, and a couple force means two equal and opposite forces acting in two different lines opposite to each other. They will create no net force, but they will create a torque. So I can mention F and F is a couple force, and a couple torque is always how much ever is the separation between them multiplied by any of the force, any one of the force. So that torque, my dear, here will be D, whatever that D is, multiplied by that F, whatever is the distance between these two lines of forces into any one of those forces is the coupled torque. This is a part of rotation from 11th standard. What is B? B is magnetic field, man. Why are you asking that question? Saharsh, the whole chapter is on magnetic field. Don't ask such questions now. I will get scared. This is magnetic field, man. The whole chapter was on that. Please watch it from the start. Hi, FF viewer. Okay. RD Vepati, why don't you put up that comment? in the comment section. I will respond to it peacefully. Okay. Yeah. Now, how much is the D? How do I find that out? Okay. If this is L, if this is, let's say L, obviously that is this side length L, then maybe if I take this particular angle as theta, this will be L sine theta. So D obviously is L sine of theta. How much is that force on any one of those elements? Well, from here, if you notice, this force will be current, whatever is there, into the length into the magnetic field. Current is I, length is W, and magnetic field is B, and into sine of 90. Why sine 90? Magnetic field and the length are perpendicular to each other, so sine 90. So it will be I W B, this force, this and this. I'm not talking about these two, anyways they were cancelling, not generating any torque. These two forces are generating torque and I'm interested in that. So in the next place, when I substitute it as I W B, let's see what do we get now. So I will put I over here, I will put L over here, I will also put W over here, and then I will put B separately. I'll put B separately, and then I'll also put sine of theta separately, and this all together is generating some kind of a torque. All of this together is generating some kind of a torque. Great. Now B is of vector quantity. I am able to see sine theta over here. I am also able to see torque, which is a vector quantity. So maybe there is another vector hidden over here, not able to see now, but there is a vector hidden over here which is cross producted with magnetic field, and I get the torque vector. Exactly what I wanted. So guys, actually the hidden vector is exactly this one, ILW, whatever you are seeing over here, this particular current into the length into the width is exactly a vector quantity, but I will have to define it as a vector, and I call this as magnetic moment. ILW is actually going to be called as the magnetic moment, and you still have magnetic field over here and still have sine theta over here. Now you might be wondering, sir, what is this M? Yes, this M, I am calling it as magnetic moment. Magnetic moment. By the way, some books also use another symbol, and that symbol is this big mu. M or mu, it's one and the same thing. It's just a matter of symbol. Okay. So other than that, nothing else. Okay. Now this M, if you notice, is nothing but current. Current is there. And L into W, what is length into W, guys? That is the area of the coil multiplied by the area of that coil. Interesting. So magnetic moment is coming out to be current multiplied by area. Now, interesting thing, if I take multiple turns, not one coil, but multiple turns on that same rectangular loop, every loop will experience the same force, same torque. And when there are multiple such windings on that same rectangle or whatever shape, the torque will also get multiplied, amplified that many times. So, if at all there were n windings, if there were n number of windings, then I would say the magnetic moment will be current multiplied by area multiplied by that n, since even the torque would have been current multiplied by area multiplied by n, and then magnetic field would have been there multiplied by sine of theta. Instead of current into just LW into B sine theta, into n would have come if there were n number of turns. So when I say n number of turns, it will be something like this. right? There are n number of turns. So because of that n turns, there will be n times more the torque. So I am calling that current into area into the number of turns as the magnetic moment, and that magnetic moment is a vector quantity. That magnetic moment is a vector quantity. What is the direction of that vector? It is simple. All you need to do is drop a perpendicular to that area. Remember, in Gauss's law also, whenever there was area, we used to draw area vector. Area vector is always perpendicular to the plane, no matter how it is oriented. So I am just going to draw a perpendicular to that area. See, our area is like this. Visualize, this is our area. This is our area. So that area vector is perpendicular to it. So this is the direction of the magnetic moment, and this is the angle theta which I am talking about, which is making it with magnetic field. So my magnetic moment, my magnetic moment in general is number of turns into current into the area. This is the formula for magnetic moment. It is a new vector quantity which I made up while solving this particular problem, and this is applicable now every single time for any loop of any shape, any size. Here for derivation I use rectangle, but even if I use hexagon, circular, any random thing, still the answer comes out to be I into area multiplied by the number of turns. Is that clear, guys? NIA. So this magnetic dipole moment has a unit of, what is the SI unit going to be? Number will not have any unit. Current is nothing but ampere and area is nothing but meter square. So ampere meter square, and it is a vector. It is a vector which is perpendicular to the plane of the area. So by chance, say for example, if my loop was like this, and if my current is going, let's say, in this manner, all you will have to do is consider this particular area, drop a perpendicular, but sir, perpendicular can be here also, correct. So take the right hand, curl your fingers in the direction of the current. What will you do? Curl your fingers in the direction of the current. So your 4 fingers you have to take in the direction of the current. The thumb points in the direction of the magnetic moment. So if you curl your fingers like this, the thumb goes here. So this is your magnetic moment. If I reverse the direction of the current, the magnetic moment will be exactly opposite. So use your right hand thumb rule. Right hand thumb rule is going to give you the direction of the magnetic moment. So what are the curled fingers giving you? The current's direction. The thumb always gives you the magnetic moment's direction. That is the logic behind it. Is this clear? It's a vector quantity and the SI unit is ampere meter square. Formula is NIA, and the torque then comes out to be mb sin theta. So if I have to formally write it down properly, first of all, look at this diagram, very interesting diagram. A current carrying loop has a magnetic moment. So to find the direction of that magnetic moment, curl your fingers in the direction of the current. Automatically you get the direction of the magnetic moment. The torque acting on any such loop, the torque which will act on any such loop this is your magnetic field, this is your magnetic moment, this is theta. The torque which will act, it will always try to rotate like this, m cross b, it will rotate it like this. So torque will be nothing but m cross producted, meaning m into sine theta multiplied by the magnetic field, m sine theta into b. So this is the formula for the torque. The second one is obviously just the magnitude part. This is the vector formula for it. Okay. As you can see, the torque always tries to bring m in the direction of magnetic field. So the torque restores the magnetic moment, in the direction of the magnetic field. Always you will see. We can take examples to see this. First case, magnetic moment is here. Second case, it is here. Third case, it is here. Fourth case, it is here. Fifth case, it is here. Okay. And then we can even further take more such examples. Magnetic moment is like this. Magnetic moment is like this. The orange ones are the magnetic moment. The pink ones are the magnetic field. You will notice always, you don't even have to use cross product. Just visualize, try to bring m in the direction of magnetic field. Here, m is already in the direction of magnetic field, so actually the torque will be 0, guys. And it makes sense because angle is 0, sine 0 is 0. So no torque will be there in this scenario. Here, there will be torque like this. Here, there will be torque like this. In fact, this torque will be maximum because sine 90 is maximum and it will be m into b. Here, again the torque will try to bring it like this. Here, I have not shown. Here, sine theta is sine 180 because angle will be 180 degrees. So sine 180 is 0. So here you will see that there will be no torque at all. So in this scenario also no torque is there. If it is aligned or exactly opposite aligned, there is no torque. Here the torque will try to bring this here. The torque will try to bring it like this. So the point is, the torque always tries to restore the magnetic moment in the direction of field. Restore it in the field. Restore it in the direction of the field. That is the job of this torque. So any loop carrying current will try to come back to the magnetic field's direction, the magnetic moment vector basically. That is the job of this torque. Is this understood, guys? Yes, Divit. Yes, man. Long time. It's been 3-4 months now. Yeah. Thank you so much. Thank you for all the love from Tamil Nadu, man. Thank you. Means a lot. Okay. Now, sir, what is the significance of this magnetic moment? Maybe you might remember we did electric dipole moment. Do you remember it? P, which was charge into the separation in electrostatics, dipoles. And electric dipole moment's torque formula was exactly like this, if you remember. It was, instead of M cross B, it was P cross electric field. Electric field is replaced by magnetic field. Torque is still the same. Electric dipole moment is now replaced by magnetic dipole moment. All these things are the same. Formulas, ideas, concepts. So what is the meaning of magnetic moment? That's what I did not tell you. I derived everything. I told you the SI unit. I told you the it's a vector quantity, how to find the direction. Yes, it is NIA and everything. But what is the meaning of it? It means it is now acting like a magnetic dipole. Dipole, two polarities, and any dipole has a moment, magnetic dipole moment. So a current carrying loop is actually identical to a current carrying loop, I would say, is very much identical to a bar magnet. Very much identical to a bar magnet. And now a bar magnet has dipole, two polarities, north pole and south pole, and that polarities will give me a magnetic dipole moment. You can use the symbol mu or you can use the symbol M, anything is fine, one and the same thing, because that bar magnet generates magnetic field lines very similar to a current carrying loop. If you'll notice the field lines are very similar, guys. Very similar. Very similar. It behaves very identical. So a current carrying loop is identical to a bar magnet with two polarities. So it is a dipole. A dipole has a dipole moment. So a current carrying loop also has a magnetic dipole moment. It behaves like a magnet. This is actually a bar magnet. This is a magnet created by current. So it is called electromagnet. So this is, I would say, a permanent magnet. This is a permanent magnet. Actually, this is a bar magnet. And this is an electromagnet. The concept of an electromagnet, you pass electricity, it behaves magnetic in nature. And you would have done this or heard about this experiment years ago in school. You take an iron nail and wind some coil turns or a wire around it, and you pass electricity, it suddenly starts attracting a lot of magnetic objects. In fact, this is also the concept used at shipyards and a lot of places where heavy cargo has to be lifted, basically those container boxes. So instead of putting that hook, unhooking it, which takes a lot of time, they use coils which have electricity in them. So if the electricity is turned on, it behaves like an electromagnet, and immediately the container gets attracted to it, and then it lifts it peacefully, drops it wherever it has to. Then the electricity is turned off, it loses its magnetic nature, and then it goes and picks up the next object. So this is the concept of electromagnet. So coil carrying current behaves like a bar magnet or a permanent magnet. That is why if this has two polarities with a moment, even this has a magnetic dipole moment. And that is what I meant by this M or mu over here. It depends on how many turns you give, how much current you pass, and what's the area. More turns, more current, more area makes it more magnetic in nature. So if you want to build an electromagnet, have a coil with many turns, with a large current and a big area. Sometimes big area is not feasible, so that's why you generally increase the number of turns. And the torque, if it is placed in a magnetic field, will be M cross D. Now, if that is the scenario, 100% even the potential energy will be the same. So if I talk about the magnetic potential energy, magnetic potential energy of a loop in magnetic field, the formula will be very similar to electrical potential energy of a dipole in an electric field, in a magnetic field. That potential energy will be minus will come, here M will come, cos theta will come, and then you will have B over here. Instead of P you have M, instead of E you have B, minus PE cos theta, if you remember. So instead of P you have put magnetic moment, instead of electric field you have put magnetic field, that's all. So strictly speaking, there is a dot product over here if you write it in proper vector form. So minus M dot B. So magnetic potential energy is minus M dot B. That is the formula. Very important. Same like electrostatics dipole moment. So that's why I said if you understand electrostatics, it becomes very easy to understand magnetism. Those concepts are very similar. Properties of magnetic fields are almost similar. Formulas for dipoles are also very similar, right? You will see later on finding the fields, the formulas are very identical. Yeah, so that is the idea. No problem, Divit, and I'm happy that you are following me here and you are watching all the classes, so it doesn't matter where I am. Always, once you are accustomed and love somebody teaching, I would to follow the same teacher, and I'm glad that you are here. Okay, so don't worry, wherever I am, I'm teaching, and I'm teaching with, in fact, the same dedication or even more dedication, still continuing my good work for all the kids who are especially from Tamil Nadu, Andhra, Karnataka, Kerala, a lot of students from Northeast and all the major cities or the English medium schools across the country and even abroad from the Gulf regions who watch these classes. I know, I've seen the analytics, most of you love watching the videos in English and not many channels do that. So I will continue, man, teaching in English. So don't worry about it. Okay, cool. Yeah. All right. So if you now look at these formulas, one thing becomes very evident. Torque is 0 in only these two scenarios where the angle is 0 or when it is 180 degrees. So these two become my special cases, this one and this one. Although this is a maximum torque case, these two cases are when torque is 0. When torque is 0, force anyways was 0. So it becomes a very, very special case that there is no torque, no force, meaning complete equilibrium. Equilibrium. The loop will not move only. So it is a case of equilibrium. Got it? Equilibrium. So that is why this one over here, the one on the top, is a case of equilibrium. This is also a case of equilibrium. But if you ask me, out of these two equilibriums, which equilibrium is more stable? I would say this one. Because if I slightly move the magnetic moment here or slightly move the magnetic moment here, the torque immediately pulls me back. So this is stable kind of equilibrium. But if you look at this scenario, if I slightly move the magnetic moment here, that's it. It does not bring me back. Rather, it pushes me away. If I slightly move the magnetic moment here, notice how the torque pushes me this side, does not bring me back. So it is kind of unstable equilibrium. Not just that, if you look at potential energy also, right, things make sense. If you look at potential energy in stable equilibrium, theta will be 0. So if theta is 0 degrees, cos 0 is 1, so it will be negative mb. If you talk about 180 degrees, meaning potential energy is unstable equilibrium, then cos 180 is minus 1. Minus 1 into this negative will make it positive. So it will become positive mb. So it will become plus mb. So this tells me potential energy is maximum. Potential energy is maximum in unstable equilibrium, which makes sense. And potential energy is the least in stable equilibrium. Has to be. Always energies potential wise are low when you are stable. You are cool, you are calm, energy is low. Yeah, they say that these days new memes have come, low cortisol and God knows what. And when you are very energetic, your potential is very high, you are very unstable. So high energy, unstable, low energy, at peace, bro. So that is what it means. So that is why I said this was anyway stable, even if you look at energy wise or even torque wise. How did I say torque? Because if you displace it this way or this way, the torque is trying to push it back. If you try to push it this way, it's pushing it back, restoring it. But in this scenario, you move it slightly here, zoop, it goes to the other side. It does not come back. That is the problem. That is why it is unstable. Okay, so that is the logic behind this. Very, very identical. Now, I have put it all this in this beautiful chart so that you can easily revise. You will get all of this in notes. So torque is m cross b. M cross b will give me the torque's direction as well as magnitude. Potential energy is minus mb cos theta. Theta is 0 stable, theta is 180 unstable. Otherwise, it is some random thing. When it is 180, it is unstable, highest energy. When it is 0 degree, you can say it is least energy. So it is highly stable. So these graphs, diagram, very, very important. Cool? Awesome. Awesome. The timing for the live usually on Friday is 6 o'clock, but hopefully in the near future I will be taking more classes. Okay. So for now, I am occupied with multiple batches also at the same time. So that's the reason why you will not see me too much also on YouTube. And anyways, now is the time for you guys to study on your own. And when that grinding mode will come from September, October onwards, then you will see more of me. Okay, cool. All right. Hello, bro, Ankur. What is this? Divit, you are a boy or girl? Man, what is this nonsense? You guys are going to decide whom to talk to based on boy or girl. I understand everything. Concentrate. Yeah, this attitude of yours will not take you anywhere. Not even NIT, not even good government college. Focus. Do all these things in college. All free time will be there. We will be doing this only most of the times. Boy or girl, there you can see, the person will be there in front of you. There you will see whether that person is boy or girl. Now you focus over here. Don't ask such stupid questions to random people on the chat. Anyways, now let's solve a question based on this. A small magnetic moment is aligned and stable, and then it is moved to unstable. How much work is done by the external agent to rotate it? So we had a coil, it had a magnetic moment like this. You rotated it and the magnetic moment turned like this. Field was still like that only. So in this process of rotating it, you would have done some kind of work. Question is how much work has been done. Now the work calculation comes from whatever work you do from external agent will go in increasing the potential energy. So finally it is in unstable form and initially it is in the stable energy form. So if you ask me, unstable potential energy, maximum it is plus MB and stable it is always negative MB. So if you take the difference, actually it will become addition now, minus will become positive. So it will become 2 times of MB. So 2 MB is option A. Got it? That's the answer. Fair enough? Awesome. Next question, let's have a look at it. A coil having 10 turns of side of a square 10 centimeters has a current of 2 amperes and its plane at 60 degrees with a field of 0.4 Tesla. Find the torque acting on it. Find the torque acting on it. That's the question. Let's try to solve it. So we have a coil which is like a square basically, and it is mentioned that, okay, let me just draw it very quickly. It is making some angle with the magnetic field and you have to find what is the torque which is acting on it. Okay, let's try to figure it out. Magnetic field is given to be 0.4 Tesla. Area of the coil we can find out because the side length is given to be 10 centimeter, which is 0.1 meter. So area is going to be 0.1 multiplied by 0.1, which is 0.01 meter square. So the magnetic moment, which will probably be like this, and we'll have to find that out to find the torque, because there will be a torque acting in this manner. So the torque we all know will be m sine theta multiplied by the magnetic field. Magnetic field we all know is 0.4. Magnetic moment, how much will it be? NIA. Remember, magnetic moment will be number of turns into current multiplied by area. How much is the number of turns? 10. So just put the number 10. How much is the current? Current is 2 amperes. Okay. How much is the area A? It is 0.01. So just put 0.01 here. Perfect. So to find the torque, I will need magnetic moment, I will need V, and finally sine theta. So for sine theta, a lot of people are just going to put sine of 60 degrees, which is wrong. That is wrong. So read the question carefully again. It says its plane is making 60 degrees, which is way different from magnetic moment making 60 degrees. Actually, these things become clear if you look at it from the side view. Yeah, if you look at it that side view, things become very clear. That loop is like this. The magnetic field is like this. The magnetic field is like this. And this angle is given to be 60 degrees. If you look at it in the side way, the plane of the loop makes 60 degrees with the field. So if that makes 60 degrees, how much will the magnetic moment vector make? That is a completely different story, man. This angle is 60 degrees. Question is, how much will the magnetic moment make with the magnetic field? That angle is theta over here, and that will be 30 degrees. This is magnetic moment, this is magnetic field. Is that making sense? So the plane making 60, the vector will make 30. Such kind of traps were also laid in Gauss law. The surface is making some angle with the electric field. What is the flux? Many times you make the calculations wrong because you took theta wrong. So be careful about that theta. So over here, my sine theta, that theta will be not 60 but 30 degrees. Is that clear? Don't take this angle. All you are going to do is take this angle. That's it. Perfect. Now we can solve the question. So it will be 10 multiplied by 2 multiplied by 10 raised to minus 2 multiplied by half multiplied by 4 multiplied by 10 raised to minus 1. So 1 10 and 1 minus 1 will go, 2 and 2 will go. So 4 into 10 raised to minus 2 is what I believe. So the torque will be 4 into 10 raised to minus 2. What is it? Newton meter. Torque is always in Newton meter. Is that understood, guys? Everyone? Very good. Very good. Amazing. Amazing. In the previous question, this one. Oh, I think you got confused. How did I write this and how did I write this? This I wrote it from here because this calculation I had done before. Stable is negative MB, unstable is positive MB. Why? Because theta is 0 and theta is 180. That makes my cos 0 as 1 and this makes cos 180 as minus 1. So from that I get unstable and stable's value. So if you remember it, it is easy, or else you can still calculate it, no? So for stable, minus m into 1 into b, so minus mb. For unstable, minus m into minus 1 into b, so it will become plus mb. So these two values, if I just substitute it over here, I will get the answer. Unstable is always higher, stable is lower energy. Minus minus becomes plus, so it will become 2 mb. And work is always change of potential energy. Now, if you don't know this formula, then I would suggest you to watch this lecture from live. See, all the kids who entered into 12th with very little knowledge of 11th and you wanted kind of a revision class, then please watch this class. I'll tell you where. I'll tell you. This one. This is the first class, backlog class for class 12 students who had missed a lot of things from 11. Watch this. This is the first class. A lot of concepts have been cleared. Vectors, Newton's laws, kinematics, everything. Then after that, this one. This class, although it says electrostatics, but there is a backlog class, meaning a lot of concepts like work, power, energy, the concept of force, power, etc. All of these were taught over here. So watch this class. These two classes, most important classes before you start your 12th standard. Okay. So after that, you will not face any of such issues. Cool. Yeah. Biot-Savart's law, next class, man. today I am focusing on forces, torques. Next class I will be focusing how did this magnetic field come. That is the Biot-Savart's and Ampere's law. Got it? So today is all about Lorentz force and dipoles and all of this. Okay, Harsh, is this clear? Where to watch previous classes also? Hi, Yash. Good evening, man. Good evening. Amazing, amazing. Now that you have understood this, let's see if we can solve this. A coil of 100 tons, is rewound. This is a circular coil. A coil of 100 tons is rewound into a coil of 10 tons. The circular coil's magnetic moment will become how many times? That is the question. It's a very good question. There is a good chance you will make a very nice silly mistake in this. There is a coil. It has 100 tons. Now you remove those windings and now make only 10 tons using that same coil. So question is, what is the new magnetic moment as compared to the old magnetic moment? How many times do you think it will change? Okay, let's visualize. First of all, this was my older coil. It had 100 tons. It also has some area. That means it also has some radius. I will call that radius as R. So it also has some magnetic moment. Let's say I call it M1, the first magnetic moment. If I write the magnetic moment, it will be number of turns into the current multiplied by area. That means pi R square. Now what happens in the second scenario? That coil is there. That coil has a new magnetic moment. I don't know, it is M2. But this time it has only 10 turns. So a lot of people, what they do, the new magnetic moment, they say it is number of turns into current into pi R square. So they say, sir, it was 100, it has become 10. So sir, it is very simple. It has become 1/10 of the first magnetic moment. That's a common mistake, guys. This is wrong because you guys will forget that I have unwound and rewound it. So how can the radius remain the same? So this is a wrong solution. Got it? This is not the right solution. So the common mistake is in the R value. So the radius will obviously change. Oh, correct, sir. So what should I do to find the radius? Volume conservation, area conservation, length conservation, think. See guys, it's a coil, it's a wire which has been rewound. So if you unwind it, there will be some length of the wire. That length will not change, no? Length will remain the same. That's it. So I'm going to use exactly that concept to figure this out. So the length of the wire is same as before. So first time there were 100 turns and each turn had 2 pi r length. 2 pi r, 2 pi r, 2 pi r, 2 pi r, 100 times. Next time there were 10 turns and each circumference was 2 pi small r. That's the only difference. Okay, now I get it. So from this 100 r is 10 r. Remove 1 0. So 10 r is equal to small r. So now when I write over here, this was actually pi r square. So I can easily see this will be 10 multiplied by I multiplied by pi. Small r is 10 r whole square. So this will become 10 multiplied by I multiplied by pi r square. 10 square is 100. 100 into 10. Great. So that will be 1000 I pi r square. If you compare this with this was 100, this was 1000. So obviously it is 10 times of M1. So M2 has now become 10 times. So it's very non-intuitive that there were 100 turns, but you made less turns over here. Funny thing is, you made the number of turns 1/10, but the magnetic moment has increased 10 times. Very non-intuitive. And the reason for that, the radius has reduced, and that has created a lot of issues. Radius has not reduced, actually it has increased. In this case, it has increased by 10 times, and that has more effect because square of the radius comes for the area calculation. Okay, so that's the logic behind it. Isn't it amazing? Hi Nandish, good evening, good evening. Sir, I have been cracked JEE. Chiku, very nice man, congratulations. Thank you for coming back over here and saying hi to your juniors and your teachers. I am very proud of you, man. Cracking IIT JEE is not a joke, and I hope you have a great life in IIT Delhi. Thank you so much. A lot of students keep coming every lecture. 1, 2 students, 2 students, 3 students are coming and saying hi, hello, and it really makes my day. Thank you so much, man. All right, Sasimina, I will be teaching class 11th also very soon, but let me find time first for it. Okay, great. So this is also done. Sir, what is the use of learning all this torque? I'll tell you what. Imagine there is a loop like this. Loop like this, having magnetic moment here. Second, let me draw it bigger. Having some magnetic moment like this, and let's say the current is going like this, and let's say the magnetic field is in this direction. Magnetic field is in this direction. So the magnetic moment will be like this. Yeah. So this is M, this is B. Now what will happen if this magnetic moment is placed in this manner in front of this magnetic field? There will be a torque acting on it. So this torque will try to rotate it, and because it will rotate, it will gain some velocity. So after some time, what happens? This loop will become like this, and it has its magnetic moment in this manner. I'm not relabeling it, but just visualize. The magnetic field is still the same way, right? Magnetic field is still the same way. At this point, yes, the torque is 0. Yes, the torque is definitely not there. The torque is 0. But what is there is angular velocity. It has now got omega because it has gained momentum. The torque has accelerated it, and because of that angular acceleration, it has got some momentum velocity. Now, if I let it go, then the moment will go like this. Torque will reverse. It will convert into deceleration, and it will slowly decelerate and stop. I don't want to do that. What I will do now, at this moment, exactly, I will flip the direction of the magnetic field. So this was the old magnetic field. Now this is the new direction of the magnetic field. I just flipped it. That is one option that I have. Or I can flip the direction of the current. Either ways. So let's say I keep magnetic field in the same direction. Magnetic field in the same direction, and at exactly this moment I change the direction of the current. So because of that, the magnetic moment also flips, something like this. The moment the magnetic moment flips because it has gone like this, yeah. This was the old direction of magnetic moment. What happens now is a very interesting thing. Observe. It has already got some angular velocity. So because of that, the magnetic moment will slightly move like this. After some time, it will go like this. Visualize. That magnetic moment will slowly turn like this. It still has angular velocity, do not forget. Now this magnetic moment 100% is going to experience a torque because of this magnetic field. It is in fact highly unstable in this region. There is a torque which is going to pull it in this manner. Oh, crazy. So as this rotates because of the torque acting on this magnetic moment, once it reaches here, I have flipped the magnetic moment. So what has happened? It's still continuing to rotate. Oh, now this magnetic moment will now get pulled by the magnetic field like this again. So this will start to rotate. This will start again to rotate like this, and it will reach this scenario. It will reach this scenario over here. Notice this is exactly this scenario over here. This is exactly this particular scenario over here as before. And it will still experience a torque which will make it accelerate. Obviously there will be angular velocity again. Again it will start to rotate, it will come here. Again I will flip the direction of the current. It will flip the direction of the magnetic moment, and that will again make the torque go like this. So in a way it will keep rotating. So this coil is now made to rotate just because of the fact that I have flipped the direction of the magnetic moment by flipping the direction of the current. So what I have got is a motor. Your fan, your electric vehicles, all of them work on this principle, man. So if you are thinking of making an electric vehicle, you should know this. Or if you are thinking of electrical technology, drones, motors, same thing. All these electrical appliances, whether it is washing machine, air conditioner, compressor, refrigerators, compressor, electric vehicles, electric motors, fans, coolers, all of them have this concept of, magnetic torque acting on a dipole moment. So this is exactly the working principle. So this is the same. So this cycle will continue. This cycle will continue. So this is nothing but how a motor works. Motor's working principle exactly is based on this. Understood? Are you able to visualize this? Yes, Divit, I will definitely be teaching 11th very soon. Just give me some time. I know a lot of you are waiting. Okay, guys. Great. I wanted to tell you this application. It's very important. Now let's go to the next concept. All right. 1 second. If I have some space. No, I don't have. Just some time back, I mentioned that if you have a current carrying loop, it is like a magnet, but because of electricity, I called it as an electromagnet. And a magnet has polarities north-south, so it is a dipole. So a current carrying loop was a magnet, and that's why I said it has a magnetic moment. Now, here there was a physical wire carrying some real current because it was connected to some battery or whatever power source. What if I don't have a current of wire? Instead, I have a charge which is moving. Imagine instead of current, there is a charge which is moving round and round and round. And if you remember, in the chapter of current electricity, we did a question like that. There was a charge which was rotating, so it was creating a current. So what is that equivalent current? We did that. So, can I not think of a charged particle revolving is like a current loop, and a current loop is an electromagnet, and an electromagnet behaves like a bar magnet which has a magnetic moment. So, a revolving charge is magnetic in nature. Take a moment for that point to sink in. It's not an easy thing to digest. A revolving charge creates electricity. It is creating or behaving like a magnet, producing magnetic moment. Now this all starts to make sense. Why Shreyas Sir at the beginning of the class only talked about electromagnetism. somewhere here. Yes, I said electric field applies force on electric charges. Gravity, very different kind of field, does not apply force on electrical charges. Magnetic field though, oh yes, it does apply force on electrical charges, although it feels the nature is different. Like I said, Maxwell and other people, they were the ones to understand that electric and magnetic forces are actually the same. That's the reason why magnetic field applies a force on an electric charge. So the converse should also be true. A charge should also be able to create magnetic field. So it was just a different perspective of looking at things, my dear. So, oh my God, so much I teach in one lecture. I am only surprised. So nice notes, no? Look at these notes, guys. Very beautiful notes, so colorful. Lucky are those people who get these notes and study from them. So coming back. So electric charges create magnetic field, magnetic moment. They behave like teeny mini electromagnets, teeny mini magnets. Probably this is the reason why any object becomes magnetic in nature. So at the end of the day, even when you have a bar magnet, horseshoe magnet, whatever magnet, it is made of matter, and matter is made of atoms, and atoms are made of protons, electrons, neutrons. These electrons are charged particles and they start spinning, they start revolving in that atoms. So each teeny mini electron revolving in an atom is a small bar magnet. A matter is made of so many such atoms, so many teeny mini magnets in that block, in that solid, in that liquid, in that gas, whatever it is. Now, if you imagine all these teeny mini magnets which are made of these revolving electrons, exactly like this, like current loops creating this magnetic moment. So now that material suddenly feels like it should be magnetic in nature. That's how magnetic properties are developed in the first place. In some materials, it so happens that these teeny mini magnetic moments end up perfectly cancelling out each other, alright, and they are either diamagnetic or paramagnetic materials. And there are some materials in which these magnetic moments end up adding together and then they become ferromagnetic materials. So your permanent magnets are those ferromagnetic materials whose magnetic moments of those teeny mini electrons which are revolving in those atoms end up adding into a resultant magnetic moment, thereby giving it magnetic property which can attract or repel permanently. But other atoms like wood, plastic, air, water, their magnetic moments do not exist or they end up cancelling each other. That's why you do not see them attracting anything which is like iron or whatever, because they do not have any net magnetic moment. So that is the concept of how magnets come into place from electricity, and all of that happens at a very minute level, at an atomic level, because of these moving charges. So to recap, if you have any charged body which has charges and it is spinning, immediately it behaves like current loops, and any current loop is going to behave like an electromagnet, which is at the end of the day magnetic in nature. So it will have magnetic moment, it will have magnetic polarities north and south. Is this clear? Is this clear? Thank you so much, Nihar, and you are going to get it on WhatsApp, not WhatsApp. I think there will be a link in the description box after a day or two. From there you will get it. Okay. Sir, are you not tired? SKMU4OP. If I get tired, then man, you will become more tired. If you see a teacher only who is not interested, then why will you be interested? And why am I interested? Because I love teaching, I love physics, I enjoy producing ranks, and I feel very happy because you just saw some time back, some kid came and told, sir, I got into IIT Delhi. And this is happening every lecture. 1 or 2 kids will come who will tell, sir, I got into this IIT, I got into this NIT, I went into this college. And these are only those kids who are coming during the live class. There will be so many other kids who don't even come or don't even tell, or maybe don't get an opportunity or don't know where Shreyas Sir is, you know. So I feel extremely happy that knowingly, unknowingly, Shreyas Sir is helping so many kids, right? So many people are becoming IITians, so many people are getting to study in English language. Otherwise, you are dependent on Hindi language, and not many people understand or are very comfortable with it. So, not just about the language, guys, I also want to give quality content. Forget about Hindi, English. Forget that. Even if you put 100 teachers, I know I will be teaching you the best on the quality content. Yeah? Alright. Great. Alright. Yes, Divit, I cannot read the previous chat now. I will have to scroll it up. Okay. So, how much is that magnetic moment? There is a simple calculation for it. See, a revolving charge has a current given by the charge divided by the time period. The time period is given by 2 pi divided by omega. So it will become q omega divided by 2 pi. Q omega divided by 2 pi. So this is the current. So the magnetic moment, therefore the magnetic moment M will become number of turns into current into area. So for a revolution, number of turns is 1, and in that the current is nothing but q omega divided by 2 pi. Area is going to be pi r square. So it will become pi cancels, q omega r square divided by 2 is the magnetic moment. So here we just had a charged particle q which was revolving with angular velocity and thereby creating its own magnetic moment. And when I say it created magnetic moment, I mean it had a north pole and a south pole kind of a behavior. Okay, so that is what has happened. Everybody clear to this point? Now what I will do, I will play around with this. I'm going to play around with this. How about figuring out what is the angular momentum of that charge? I know you are wondering what the hell is angular momentum got to do with all of this. Anyways, let's just find out what is the harm. You will see what the magic is. So let's try to figure out what is the angular momentum of that same charged particle. Angular momentum is moment of inertia into omega. Moment of inertia is just m, mass of the particle, into r square into omega. Great. Now what I am going to do is the interesting part. Now divide magnetic moment. Now divide magnetic dipole moment, or just the magnetic moment, by the angular momentum. And see what do you really get. Therefore, magnetic moment is m, angular momentum is L. Magnetic moment q omega r square by 2. Okay, q omega r square divided by 2. Angular momentum mr square omega. Great. A lot of things are getting cancelled, and what I am seeing is m by L. R square gone, omega gone, q is there, 2 and m is there. Oh, but don't get confused, this is mass, not the magnetic moment. So let me use small m, else you will get confused. So it was q divided by 2m. Now this is a very interesting thing. It is independent of omega, independent of the radius, right? It is just one nice peculiar constant value charged by the mass ratio, which is a specific charge per unit mass kind of thing. If I know L, I can easily find M. So this formula is very important. It is called as the gyromagnetic ratio. So it is not just valid for a charge, but you take a set of charges. A rigid body with some uniform charge distribution, and let it rotate, man, about any axis, doesn't matter, let it rotate. It will have its angular momentum and it will also have its magnetic moment. It will also have its magnetic moment. So there will be magnetic moment, and at the same time it will also have angular momentum. So if you divide the magnetic moment with the angular momentum, what you will always get is how much ever total charge is there on that body, so I will call it Q, upon 2 times the total mass. This is always a constant irrespective of the speed. This is called as the gyromagnetic ratio. Gyromagnetic ratio. Is that right? So it doesn't matter what the angular speed is. This can be used to calculate anybody's magnetic moment quickly. Anybody's. So right now, this object, just because it is charged and it is rotating enough, it has now created a north pole and a south pole. So this is like a bar magnet. That's it. It is behaving like a bar magnet. That's all. This is the same thing. This is behaving like a bar magnet. Perfect. Let's take up examples of this so that you get an idea of how to use it. There is a disk of some radius, has some charge density and is rotating with some speed. What is the magnetic dipole moment? Alright, let's figure this out. We all know magnetic moment by angular momentum is the total charge divided by 2 times of mass. So if I want to find m, keep q by 2m as it is, just shift L over here. What is the purpose? Finding L is easy. Yeah, it is easy, man. How? Let's figure it out. So it is q divided by 2m. Angular momentum is moment of inertia into omega. Is that right? Okay. So this will be q by 2m. What is the moment of inertia of a disk? Oh, it is m r square divided by 2. Here the radius is capital R, so let me use the same symbol. That's it. And into omega. Got cancelled, 2 2s are 4. So therefore, magnetic moment is q r square omega divided by 4. Is that right? But I don't see such answer anywhere. Because something else is given, they have not given the charge, rather they have given the charge density. So be careful. Now the charge density is how much ever charge is there by the area, which is pi r square. So q is sigma pi r square. Oh, so just put sigma pi r square over here and rest will follow. R square as it is, omega as it is, 4 as it is. Therefore, magnetic moment will be sigma pi r raised to 4 omega divided by 4. Sigma pi r raised to 4 by 4 is the option number A. That's it. That is the answer. Very simple. So this rotating disk is behaving like a bar magnet whose magnetic moment is this much. Formula q by 2m is m by L. Why did I use it? Finding L is easy because L is I omega. And finding I is very easy because you know the formulas from rotational motion. Got it? So this is the easy method to find magnetic moment. One shot for current electricity. Why do you want one shot, man? Guys, this is the wrong approach. Who has taught you all of this? Listen to one shot right now. I have taught a detailed classes, 5.5 hours class. Watch this. Why do you want one shot? One shot means 1 hour you want to finish the chapter. For revision, it's okay. Have you completed the syllabus? Then you watch one shot. You might find it on the YouTube. But now you have time. Yes, you have time. It is just July. August is there, September, October, November. Then you can complete the syllabus. Still you will get 2 months for revision. That too for first attempt. Then you have second attempt. So don't hurry up. Especially a chapter like current electricity, which is so important. I have taught it in detail. Watch it. Okay. And even capacitors is a separate thing. That I have taken another 5 hours. I am telling you, capacitors usually teachers will ignore. But capacitors is important. It comes so many times with combination with current electricity. So it's not just current electricity. Capacitors comes as a part of current electricity and a special part of electrostatics. That Gauss law, plates, etc. part is electrostatics. But when it comes to RC circuits, then it comes to current electricity. So I've taught that also, charging and discharging of capacitors. So watch all of that. Got it? Okay, great. Fair enough. Let's move to the next question coming up on your screen. And what is this? A non-conducting ring of mass m uniformly charged with Q is spun along its principal axis with constant speed magnitude of the equivalent magnetic dipole moment. Same logic as before, guys. M by L is charged by 2 times of mass. Therefore, magnetic moment is Q by 2m multiplied by angular momentum. And angular momentum, my dear, is simply I into omega. Now, I know the value of moment of inertia for this particular object, which is a ring, which is just m into r square, and this omega is say as it is. M cancels, so it will become q r square omega whole thing divided by 2 is the magnetic moment. Q r square omega by 2. Q r square omega by 2. Oh, option A. Option A is the right answer. Very good, very good, very good. What a perfect thing. So that's the logic behind this. Is this clear? So that was the last part. I know I have one more thing, which is magnetic moving coil galvanometer and all of that. Maybe I'll take it as a separate lecture or separate thing later on with galvanometer, voltmeter, ammeter, potentiometer separately some other day, right? So don't comment now, sir, you did not teach moving coil galvanometer. So that usually I do it with electrical instruments, voltmeter, ammeter, potentiometer, all those things. Okay, so don't worry about it. This was the main part of the chapter, and we have done everything apart from the moving coil galvanometer. So after this, you will be able to solve literally every single question. There is no concept which is left from this part of magnetic field and Lorentz force. Next lecture we will do sources of magnetic field, which involves current wires field calculations using Biot-Savart's and Ampere's law. So solenoid, toroid, all those things will come later on. Okay, cool. So that's it from now. And I hope you enjoyed the class and hope you were attentive. And if you are not attentive, please watch the part which you are not attentive. Watch these classes regularly because Shreyas Sir is giving these notes in a beautiful form for all of you. PDF will be available after some time. Check out the description box and stay tuned on the channel. Yeah, if you're not yet subscribed, subscribe because or else you lose out all this nice stuff, okay, for your JEE. So gear up, guys. There is no stopping now. There is no staying back. It's just moving forward. And if you fall back, you will lose the momentum. So please gain that momentum. Thank you. Bye-bye. Take care.